what I'm going to do is I'm going to start off by, of course, we'll talk about the solution to, oh, this is always pops up here. Okay, so this is very quickly slideshow from beginning. No, guys, look, I do know who goes through the trouble of doing the assignments and who doesn't. I mean, that's one thing I like about Leah. It tells me who downloaded the assignments and all that. So do yourself a favor, you know, do the work. I mean, okay, so design a built-up column for the following parameters. So this was we had a dead load of 0.4 kPa, a live load of 1.5 kPa. We had a tributary area of 22 square meters, an unsupported length of 2.2 meters, untreated and dry service conditions, column effectively pinned at both ends, and of course use SPF number 3 lumber. So basically for case 1, what we have is we simply multiply by the dead load, which is very, very small. Now, for case number 2, because I've exceeded 20 square meters, if you want, you can take advantage of the live load reduction factor. That's up to you. You got no obligation to do that, but as soon as you exceed 20 square meters, you can use the live load reduction factor. And it kind of makes sense, guys. Guys, you have to remember, it kind of makes sense because, okay, like here you're talking about 400 square feet, okay? That's the limit, you understand? 20 square meters is about 400 square feet. In other words, 200 square feet. 10 times, yeah, 200 square feet. So what's the probability that all your 200 square feet are going to have the live load completely on that area? Now, where this becomes very important, okay, is when you have a multi-level building, okay, and you have one column sitting on top of another column, sitting on top of another column. So now you can appreciate that here you have, like, the areas keep adding up. So like for this column here, this is the area and that's the area. So therefore the live load reduction factor becomes significant. And then for this column here, this is the area, that's the area, and therefore when you calculate the live load on this column, so this is where these live load reduction factors become very beneficial. Like you can appreciate when you have a 25-story building, well, you know, when you get to the bottom of the 25th story, the areas become quite significant. So for that column there, like the fact that all these floors are going to be loaded to that capacity are very, very, you know, the probability of that happening. So that's where it becomes very, very beneficial. So the higher the building, the more columns you have, that's where the live load reduction factor can really help, okay? Just letting you know. So now, so here I go. So this is the formula, 0.3 times the square root of 9.8 divided by the tributary area. And like if you put 20 in here, you'll get an answer of 1. So that means under 20, you shouldn't be using a live load reduction factor. At 20, it makes no difference. As soon as you get over 20 square meters, you will get some reduction. In other words, the value will be less than 1. Here I get a value of 0.967. And therefore, I use it and I multiply my live load with the live load reduction factor, thereby making my total factored load 2.68 kPa. Now that I've got that, I know that the analysis is very simple. The factored axial force is equal to the factor load times the tributary area. Therefore, I take 2.68 times 22 square meters. That gives me my PF. Now, of course, we always want to make sure your PR is greater than PF. If you look at the table, yes, we're dry. Yes, it's standard. Yes, it's yes. So we can go straight to the built up. We have an unsupported length of 2.2 meters. Now, if we go to built up columns, okay, so here we have, for example, if you want to use 2x4s, which is perfectly okay. And of course, 2x4s, you want to be able to, so what you're worried about, you worry about the grade, of course, the species, make sure you're in SPF. This table is for SPF. I'm sorry. So therefore, I'm at 2.2 here, okay? And if I want to use 2x4s, well, I would have to use a 4-ply if I'm using 2x4s. I have a PR of 6.2, so that's one of the good answers. And the other one is, of course, if I want to use 2x6s, well, if I go to 2x6s, and the same thing, the height is very important. And of course, looking for P, oh, here we go. PR is 60.7. So with 2x6, I can get away with a 3-ply. Okay. Now,
Understood.
yes.
If, for example, if you have a length of 2.44, can you just go with the 2.6, or do you want us to interpolate?
If you want to be conservative, you should use 2.6. If you have
Okay.
2.44, if you want to be conservative, if you want to, if you want to take a chance and take a chance, and the old expression, take a chance and sit by the seat of your pants, uh, you know, you can use 2.4, and then if you want to be more accurate, you can interpolate between the two. You understand?
Okay.
It all depends. Like for example, if you're telling me that your PF is very, very close to your PR at 2.4. So it's a question of judgment, Adam, you understand?
Okay.
What I'm saying is that uh, let's say I'm doing this in real life. I really have a length of, it's unfortunate because 2.44 unfortunately is a very standard length, okay? And don't forget, we're not talking about a big difference, okay? Now let's say
Okay.
my PF value is, I don't know, 18, you understand?
Mm-hmm.
Right? And I come here and I see that it's 20.5. Well, I feel comfortable. You understand? But if my PF value was 20.4, you understand? And I come here and I have 20.5, well, I don't feel very comfortable. So that's
Okay.
another,
Good.
you understand? So there's also a question of judgment. And ultimately, if you want to make absolutely sure, okay, uh, you got to appreciate something, Adam. I don't even use these tables. You understand?
Okay.
What I do is I have an Excel spreadsheet, and you know those formulas, PR and PRA and PRB, right?
Mm-hmm.
I just put my values in there and it gives me the value right away. So no matter what length I'm talking about, I get the value right away. You understand?
Yeah. Perfect.
So that's that. See, these tables are convenient if you're not, but the fact that, and of course these tables were very convenient for me in the old days, that instead of me having to calculate everything, I can get a value straight from the table. But today with Excel, it's so easy to set everything up. But mind you, it's not worth it for you guys to do it because you're only going to do it once. But for me, that I might be doing this like 2-3 times a year, I'll call up my Excel spreadsheet, put the value in, and get my value. You understand? And at the same time, I know that I've used this sheet over and over again. And of course, I've compared it with manual calculation, compared it with the values in the table, make sure everything was good. And it also helps me minimize making a mistake. So,
Okay.
you can see that you can appreciate that. So therefore, like here, like I said, there's two answers. They're both right. Now, which one is more right than the other? Well, if your wall is made with 2x6 studs, of course, you should be using 2x6 built-up column if the column is going to be sitting in the wall. If you're using 2x4 studs, you should be using a 2x4 column if it's sitting in the wall. Okay. So that's, like
So wait,
there's
sorry,
no,
sir.
yes,
Why don't we use 38 by 89?
we did 38 by 89. We did. It was a 4-ply.
It was a four. Okay,
We
never
did.
mind.
That was the first one I went to. So here you go.
Oh, okay, it was the
SPF.
first.
Yeah.
Okay,
And I said with a length of 2.2, we had a PR of 60.2.
yeah,
And it's
okay,
great. Okay, so if you're using a 2x4, you have to have 4 plies, and then if you use a 2x6, you only need a 3-ply. Okay. Now, which one is cheaper? I think the 2x4s, it'd probably be about the same price. I'm not sure. Okay. Now, just remember one thing. Okay. So PR. Okay. Now, in this case here, I don't ask you to check QR. Okay. But remember, when the column is between sill plates, you should always check that your QR is greater than your QF. Okay. So in other words, if ever you're building a column and it's sitting inside, uh, like in other words, what I mean by sill plates, for example, I have a sill plate at the bottom here. Okay. And I have like sill plates at the top. Doesn't matter where they are because it's going to be the same QR value. Okay. And of course, if my column is sitting in here, okay, in that case, I have to check the QR. Okay. If the column is sitting on a piece of concrete, well, I don't have to check the QR because it's concrete. Okay. And of course, if the column is sitting, if a wooden beam is sitting, if the wooden beam is like what we have in a project, if your wooden beam is sitting on top of your column, well, you're gonna have to make sure that the QR, you have to check the QR, and that's what we'll do in the lab. Okay, I'll check that very quickly with you, and I'll show you how simple it is. It's not very complicated. Okay, and I think that's pretty well it. Anybody have any questions before we move on? Pretty well clear? Okay. I think that's it. I'm sure this is the end of it. Let me, oh yeah, the end, there you go. Okay, so that's it for the assignment. Now let's go to the lecture and let's learn something really good today. Okay, share, and oops, I should have, sorry about that. And show, okay. I might as well close this, get it out of this thing. Stop sharing. Okay, let's go to, ooh, where are we? Share, there, share, and I want, where's that PowerPoint? There you are. Yeah, that's going to be for the lab after. Okay, so today we're going to learn two things. Okay, well, two things. We're going to learn, the first one is very simple. Okay, today we're going to learn about tension members. Okay, and of course, tension means that the fibers are being pulled apart. Okay, so in other words, the wood is being stretched. Okay, and where do you find a lot of tension members? Well, in trusses, a lot of the web members are in tension. The bottom cord of a truss is in tension, and so on and so on. Okay. If ever, you know, like if ever you guys, anyways, if ever you guys want to, hold on, let me just annotate, okay? If ever you guys are planning to use some kind of wood here so that you can make a hole and you want to put a noose here and you want to hang somebody, well, you'll be able to determine what the size of your member has to be. How's that? Okay, so this is going to be in tension. So it's all good stuff, okay? So, and we're going to learn about combined loads, where we have both axial loads, both compression and tension, and bending moments. And that's where it becomes, you know, interesting, because this is for, you know, columns that are eccentrically loaded and so on and so on. So we'll start off with the tension members. And so the following design information for the members are used in tension parallel to the grain. Again, okay, guys, always remember that when it comes to wood, okay, the wood, if you guys don't know this, you should know this by now, okay? The wood has a general grain, okay? So it's like, so in other words, here what they're saying is that if you're having a tension force on this member, it is about parallel to the grain. In other words, you're not looking at tension this way, okay? Because this is going to split your wood, okay? So the resistance here is much different than the resistance there, okay? So wood has, the fibers have a resistance depending on in which direction they are being, you know, stressed, and therefore it's going to be parallel to the grain. Just like when we talked about compression members parallel to the grain, okay? Except for bearing, then, you know, for QR, that's always perpendicular to the grain. Okay, so that's one thing you have to keep in mind. Now, the amount of material removed due to fasteners and grooves must not exceed 25% of the gross area of the member. So what they're saying here is, if I happen to have a member here, okay, and I need to make a hole for whatever reason, okay, well, that hole cannot take away more than 25% of that. Okay, the material that the hole takes away, okay, cannot exceed 25% of the area of the member. Now, guys, remember, I don't know if you guys know this, but for me, it's very simple. I mean, here's my member. Oh, sorry, I should have, I like to draw with this better. I know it's not as straight, it's fast for me, okay? Now, remember, this here is the B, okay, or the B of the member. This here is a D, okay. Don't forget, for the hole, you have the same D. So therefore, all you have to subtract is all you have to do is subtract the diameter of the hole from D, and that's the percentage. You don't have to calculate the area of the hole, okay, because this is a constant. So that means that if I have a 2x4, okay, which is a 38 by 89, all right, and if I take 25% of that, I don't know what that is, so a quarter of, well, 28, okay, so 0.25 times 89, okay, so this hole cannot be any greater than 22 millimeters, okay? If it's greater than 22 millimeters, you can't you can't use this these formulas. Now, why do they restrict you? It's very simple, okay? Because where you have holes, okay, where you have holes, you have, like, whenever you guys are designing anything, you're assuming that all the stresses, like for example, the tensile stresses here, you're assuming that they're uniform, okay? You're assuming that they're uniform, and that's an assumption, okay? Because, but that's what you're actually doing. Now, where you have a hole, of course, what's going to happen is that you're going to have a concentration of stresses around the hole. So therefore, the stresses are going to get bigger around the hole. And then after that, eventually, they'll become uniform. So in order to give the stress to become uniform again, to be able to use this formula, they don't allow you to exceed 25% of the material, okay? And that's all it is. Now, that's if you have to make holes to put your fasteners in. So in other words, if you're putting a bolt in, if you're putting a lag screw, whatever it is. If you're nailing, well, nailing, you don't remove any material. You're simply driving the nail in the wood, therefore not a problem. So any nailing is not a problem. It's only if you have to, like a drift pin, a bolt, a lag screw. When we get into fastener, I'll show you all these fasteners. You'll understand what I'm talking about. So that's one thing you have to keep in mind, 25%. Okay, for tension members. And like I said, if you're nailing, it's not even an issue. Okay, so now the design objective is always, of course, the tensile resistance, TRN. Now we use N here because we're talking about the net area. And of course, if you're nailing, TRN and TRG is the same thing versus the factor tensile resistance, TF, okay? Now, TRN, of course, is TRA, A net over AG, okay? So in other words, you take your net area divided by your your gross area, you get that ratio, and make sure that that ratio does not exceed 75%. And then the TR value, okay, that you get from the table, that becomes your final total resistance of the net area. So if you have nails, TRN and TR are one and the same. So don't worry about that. If you're making holes with a drill to pass whatever fastener, then you have to worry about taking this ratio and when you get the value from the table, make sure you reduce it by this ratio. Now, TRN, the factor tensile resistance of the next section. And of course, the factor based on the gross section. Okay, so in other words, there's no holes whatsoever. And of course, the tables are based on TR. Okay, now a net area, which is the gross area less the area removed due to the drilling, net area must not be greater than 0.75 AG, of course, like I said. And like I said, the hole goes right through the whole member. You just have to worry about, like the diameter, and you just take the diameters, the diameter versus the width, and it gives you the same ratio. You don't have to go calculate AG. You just calculate on the width of the member. And of course, AG is the gross area. Now, so like I said, now here's a checklist you have, okay? Here's a checklist you have in order to use a table, okay? So to verify that the tabulated radius is appropriate for the structure being designed, the following questions should be asked, okay? Is the load duration standard? And of course, if you're building a house, the answer is yes. Is a tension member acting as a single member? Okay, if it's no, then you can modify the resistance by KH. Is the surface condition dry? Yes. Is it okay? Yes. So if it's all yes, then of course you can go straight to the table. So now, this is the formula. Okay, this is the formula. And of course, I don't like to do much with the formulas, and especially since these tables, I can modify the values in the tables just as I did in the joist tables. In other words, there's a linear relationship. It's not like the compression members, which I have to, if I answer no, I got to do everything by the equations. Here, I'm not worried about the formula because I know that this FT here is based on, these are the factors that affect the FT here is the small FT times all these factors, which is the duration, the systems, the serviceability, and treatment. So therefore, right away, I know that I can modify this linearly, and therefore, just like the joist tables, I will modify the values in the tables depending on whether if this is 0.65, if this is 1.1, if this happens to be whatever 0.85, and so on. Okay. And I'll show you what these factors are, okay? So FT is the specified tensile strength based on the cross-sectional area, AN is the area, and KZT is the size factor. Now, you don't have to worry about that because the table already incorporates the size factor. And here's a checklist. So we said, like, if KD is standard, this is 1.0. If it's a single member, of course, it's 1. If it happens to be a case 1, therefore I can multiply all the values by 1.1, just like in the joist. And if it's, okay. Here are the modification. Okay, so here's the table, okay. So you have a table here where you have, okay, let me talk about this because this is the first time I think you guys see this, okay. So basically we're here, this the species that we tend to use in Quebec, okay, number 1. And of course, this is a 2x4, 2x6, 2x8, 2x10, and 2x12, okay. Now, as far as the visual grades go, I would not necessarily go with structural select. If it's a 2x4 and a 2x6, most likely I will use this. But if you're making trusses, you can also use number 1, number 2. It is available, okay? So these are the visual grades. Now, machine stress rated, okay? What this is that the lumber, okay? This is the lumber, like this, okay? And it passes through a machine that actually, okay, this is what I like about this. It passes through a machine that actually, where is that? Okay, that actually, oops, I should do it the other way. Sorry, let me clear that. Erase. Okay, this machine actually applies a force at every 6 inches. The board goes through the machine actually comes down and applies a force, okay? And that force, they know for that force, what's going to be the bending resistance of this member. So for example, if they wanted to be rated at 1450, now 1450, guys, I don't want you to, okay? This is PSI. This is the bending stresses in PSI. In other words, this is 1450 PSI bending stresses for the wood. Now, if you guys want to do calculation by bending stresses, you're more than welcome. And these are allowable bending stresses, so you don't even have to factor your loads. And of course, this is the modular elasticity. So you can see that. So what happens that this, as a matter of, these machines will actually test 1,000 feet of board a minute. That's how fast it goes through the machine. 1,000 feet a minute, okay? So it goes through this testing machine, and if it comes out uncracked, well, it gets stressed like that. So you can appreciate, for example, and I know that a lot of truss manufacturers, they like to use machine stress rating because this way they'll be able to minimize the amount of work. So if you look here, okay, for example, like this is very hard to find, okay? But if you look here, for example, if I machine stress rate the wood, okay, even for, excuse me, even between, for example, a number 1, number 2, okay, and a 1450, you can see that the value is better. You understand? This is the TR value. Here's the TR value. When it, like in other words, it can go up to 24. So like in other words, this is pounds per square inch. Okay, this is pounds per square inch, and this is allowable stress. So we never talked about allowable stress. That's no longer allowed in Canada as a design method, but in the States, they still use allowable stress. So this is 2,400 PSI allowable stress. This is 1,200 PSI allowable stress, and so on, okay? So you can see that the reason why it's very nice is because, like, for example, if it's a number 3, you're down to 14. So if I can get, for example, I've seen trusses with, you know, like they might use, you know, they might use 2x4s with this machine stress rating. So you can appreciate that even for structural select, you see, 39, well, now you're up to 53. If you go up to 2,400, you're up to 66, the TR value, okay? So you can appreciate that the machine stress rating, instead of relying on the grader who actually just looks at the defects and gives it a marking and says what it is, well, these machines will actually load test the lumber, and then if it comes out uncracked at the end, well, then it gets rated for that stress level, okay? And that's what these are. So like, it's available, but like most lumber yards will not carry this. This is like, it's done. And most people that use machine stress rated are the ones that might fabricate the trusses for the houses, because they take advantage of the fact that they'll be able to use a higher resistance and therefore end up saving some money on the wood when they fabricate the truss for the house. Okay, so here is very simple. Okay, so depending on the size, depending on the species, you get your TR value. I mean, just like, you know, in the Joyce table. And the only thing you have to keep in mind is that this is all for single members. Okay, if you happen to have a system where you have 3 or more members, not spaced more than 600 millimeters apart, like for example, roof trusses, then you can take the values here and multiply them by 1.1. And that's all you have to do. Any questions on this table before I move away? It's all good?
Yeah, I guess. Yep.
Okay. Okay, so there's your table for TR. Okay, now KD is the load duration factor, and we've seen this. Okay, so KD for standard is 1.0, for permanent load is 6.15, and for a short-term load, 1.15. So when you're designing for wind, when you're designing for formwork, it's short-term, you can take advantage of the KD equal to 1.15. Now, KH is a system factor. What's a system factor? We talked about this in Joyce, the same thing. You have at least 3 members. The tabulated resistance are based on a single member. Okay, for case 1, so what's this case 1 system? If you remember, we have at least 3 members that are generally parallel to each other and spaced no more than 610 millimeters apart. If that's the way that your structure is being framed, then you have a case 1 system, and you can take the values in the table and multiply them by 1.1. And then KST is a service, of course. For dry, it's 1.0, okay? And for wet, 0.84. So that's for if you happen to have wet wood and it happens to be in tension, well, then it drops down to 0.84. And of course, KT, your treatment factor, whether it's treated or incised lumber, it makes no difference in this case, as opposed to a compression member. KT dry 0.75, KT wet 0.85, okay? And like I said, if ever you're using a very strong chemical for fire retardants, call up the chemical company and ask them for the KT value. Okay, these are suggested values, okay? Like that will cover most cases, but if you want to be more accurate, get the information from, or get the guy that's actually treating the wood and ask him what the KT value is. That would be the best way to get the right values here. Now, let's do something simple. Design the bottom chord of the light frame Gus plate connected trusses for the following conditions, okay? Now, you have a factor tensile force of 16 kilonewtons. So in other words, that's how much is pulling on the bottom chord. And you have dry service conditions and untreated lumber. Of course, it's going to be inside a roof space, so therefore it's going to be relatively dry. It's going to be untreated. The trusses are spaced at 600 millimeters on center. So you know that when it comes to a roof truss, in order to cover the whole house, you'll have at least 3 trusses and more. So therefore, you're having a case 1 system. And of course, here we're going to use number 3 stud grade. Now, I would suggest you can also use number 2, you know, number 1, number 2. And for the project, I will suggest we're going to be using number 1, number 2. It's available. It's not as available as number 3, but you can get some. So now we go to the checklist and we'll ask ourselves, is load duration standard? Yes. Is a tension member acting as a single member? No, because we have at least 3 trusses on the roof. So the answer is no, okay? Is the service condition dry? Yes. Is it material free? Yes. So therefore we have 1 no here, okay? So what we can do is we can go and modify the values in the table. So we can go and modify the value by the KH value. Okay, and we saw that before that it's 1.1. So what I can do is, just like we did for the trusses, I take my TR value is equal to my TF divided by my KH. And in this case, it's beneficial. In other words, I go from 16 kilonewtons and I drop down to 14.5. So when I go to the table, I'm no longer looking for 16, I'm looking for 14.5. And therefore, I go to the table and see what I need. So if I go to the table here, I need, we said number 3, so we're here, okay? Now you'll see that if I didn't take advantage of KH, I probably would have said a 2x4, okay? That's what I would have said if I wouldn't taken advantage of KH. But because I have a KH value, I drop down to a 2x6, I drop down to a 2x4. And that's the advantage of, you know, modifying your forces according to what you're allowed according to these factors. So if people wouldn't have modified the sorry, the TF value by 1.1, then they would have come here and they would say, I need 16, well, I'm going to use a 2x6. No, you can actually get away with a 2x4. Is that clear to everybody? Now, if you use a 2x6, of course you're going to be right because it's TR is greater than TF. But in reality, I mean, if you want to save a few bucks, well, the 2x4 would have been adequate for your design. Okay? Any questions? I guess not. Okay. So SPF number 3, 38 by 89. I have a TR. Okay, so the TR value is 16.4 over 14.5. I'm okay. Like I said, if you wouldn't have taken advantage of it, you would have ended up with 38 by 140. Okay. Now, if I give you a problem like this on an exam and you happen to not take advantage of the fact that you can modify the value, okay, well, I'm not going to mark it totally wrong, but I'm going to penalize you because you haven't really, optimized your choice. Because, as long as the TR is greater than the TF, nobody can say you're wrong except for your client that is spending more money for the wood. Before I move on, any questions here? Are you guys still there?
Yes, sir. No questions.
Okay, no questions. Okay, guys, look, I mean, by all means, it's kind of hard for me. All of you have your videos off, so it's kind of hard for me to know if you're there or not. I'm talking to myself. So, okay, so here we go. Thank you, Nermin. I see the top of your head. Look, I see your forehead. So, thank you, Nermin.
If you see the rest of my face, I can't see the screen. That's why, but I'm here.
I know. As long as I see your forehead, I know. Now I see your eyes. How's that? Fair enough. Okay.
Yeah, I'm here.
Okay, now, combined loads. Combined loads is a situation where you have not only an axial load, in other words, tension or compression, which are axial loads, but you also have a bending moment occurring, okay, at the same time. And of course, combined bending and axial compression occurs in top chords of trusses as well as in laterally loaded studs and columns. So what this means is that when you have a truss like this, okay, because this member is continuous, you are going to end up getting, you're going to end up getting bending moments in here like this, as well as an axial compression force in there, okay? And then also for tension members, if this is continuous, you're going to end up getting bending moments in here. So this is where you end up getting combined loads. And also we're going to do this, I think this is the next class, where we have the exterior wall, we have a gravity load here, and we have the wind load here, okay? So this becomes a combined load. Okay, so in other words, you have the wall is being subjected to compression force and the winds are creating a moment. So the two of them together are acting on the member, and therefore the member has to be able to resist the stress caused by the axial force and the stress caused by the bending moment, okay? And that's what we mean by combined loads. Now, members subjected to combined bending and axial compression forces or tensile force must be satisfied the appropriate interaction equation. So this is the two interaction equations, okay? PF over PR squared. In my days, believe it or not, in my days, this was not here, okay? This was not here. This helps you. By squaring this ratio, it lowers it, so it helps you, okay? In my days, what they found is that because of the knots that there is in the wood, wood has these knots, okay? They found that the knots helps to improve the compression force of the wood, and therefore they were able to bring this to a square. Anyways, you can see that research does pay off sometime, okay? So, and of course, MF over MR. Now, what this is, okay, this is basically an amplification factor, okay, which amplifies the bending moment, because what happens is that here's my column, okay, here's my column like this, right? Here's my axial load like this, okay? Now, when this thing is bending, okay, believe it or not, these axial loads contribute to the bending moment, because this is no longer acting in the centroid, and that's what this does, okay? It actually amplifies the moment to compensate for the axial load that is no longer acting on the centroid, because the centroid is moving out of place by the bending moment. So, and that's what this is, okay? And that's got nothing to do with its wood. It's the same for wood, for steel. Of course, each material has its own way of calculating it, but it's the same concept for every type of, you know, column that has a bending moment. So we're going to see that, like when we're going to be doing the exterior columns for the steel project, we're going to see this as it's done for steel. Here we're seeing it as it's being done for wood. Okay, and this equation here we're going to be using to design all our exterior columns for that are going to support the lintels in our project. Okay, that's where we're going to be using this extensively, because those columns are going to be subjected to a bending moment caused by the wind and an axial force from the lintel above. So this is for compression, and of course you have one for tension. Okay, TF over TR, MF over MR. Okay, now guys, these look complicated, right? These look complicated, but look, it's not very complicated. What's the design objective all the time? We want to make sure that TR is greater than or equal to TF, right? What's TR over TR? That's 1, right? 1.0. So therefore, TR over TF, okay, has to be, okay. So basically what you're doing is that you're taking this, okay, you're taking this ratio, if it's acting by itself, and that's what you're doing once, and now you're putting a moment. So the two of them combined, the two ratios combined have to be less than 1. And that's all you're basically doing. So now you're not, because what happens, like, I don't know if you guys know this, but okay, let me do, if I happen to have, you guys know that this is my member. I'm going to do this. I'm probably going to confuse you more than anything else, right? Here's my member. Let's start with a tension, or let's start with, yeah, let's start with tension. I have tension here, tension there, right? Okay. So what happens here, the tension is, if I break this piece here, I have tension there. So here I will have inside the wood, this is what the wood is doing, right? Okay. It wants to, you know, you're pulling the fibers. So that's, now, when you happen to have, now I shouldn't do this because sometimes I do this and it confuses more, okay? Now, when I have a member, I'm gonna change color, okay? And now I gotta change color. I wanna change color. Now, I've got a bending moment. Okay, I got a bending moment. So what does a bending moment do? It causes tension on this side, it causes compression on this side, right? So on this side, I got tension. And on this side, I got on this side, I got tension. And on this side, I got compression. So here, these add up. Here I have compression, okay? So these add up. So therefore, you have to make sure that this plus this, that's what you're doing this, doesn't exceed the maximum resistance of your wood, and that ratio has to be less than 1. That's all you're doing. And the same thing happens when you have compression. In other words, when you have compression, everything's the other way around, and that's what you're doing. So that's all you're doing. The interaction means that the stress is caused by the tension, and the stress is caused by the bending moment. When you take that with the total resistance of the member for tension, that ratio has to be less than 1, and this is what happens in compression. In other words, this is the actual compression force, this is the bending, you know, so therefore, and compression members becomes more critical because you're adding the compression caused by the axial force, and you're adding the compression caused by the bending moment, and those two compressions together, they cannot be greater than 1. And all this does is that it amplifies the additional moment that is created by the fact that the axial force is no longer acting on the centroid of the member. And that's all this is. It looks very complicated, but when you start realizing what's happening, it makes a lot of sense. So that's what that is, okay? Clear all drawings. So now, so here you have PF is the axial compression force, TF is the axial tensile force, MF is the bending moment, PR is the factor compression resistance parallel to the grain, TR is the factor tensile resistance parallel to the grain. So sometimes you can find these values straight from the table, depending on the situation. MF, of course, is the bending moment. And PE, of course, that's the Euler buckling force in the direction of the applied moment, okay? So this is, okay, now how do you calculate PE? Well, there's a formula for that, like I said. So here's the formula for PE. Pi squared EO5, in other words, this is the modular elasticity of wood in compression, okay, to the fifth, this means to the fifth quintile, percentile, okay. I is, of course, the moment of inertia, you know, which is 1/12 the base times the height. Squared, yes.
You had 2 MFs.
Sorry?
You had 2 MFs.
I had 2 MFs before?
Yeah.
Okay, so here I should have, this should be MR, okay? So this is the, I'm sorry, yeah, so this is wrong. I should go back and correct it. So let me, oops. So this should be MR. Sorry about that. That's a, you see what happens when you cut and paste, but I put factor bending resistance, so that's MR, right? Did I already, I haven't sent you the lecture yet, have I? So that's good. Pardon?
No,
So-
you didn't.
So therefore I'll send you the corrected one. How's that? So I apologize. Like I just cut and paste. I forgot to change the MR. So thank you for correcting the typo. Appreciate it. And slideshow from current slide. Okay, so back to this. Okay, so thank you. So I put factored bending moment resistance, so that should be MR. Like I said, this is the equation to calculate PE, okay? And of course, this is going to be in newtons, therefore you have to, you know, divide by 1,000 to get in kilonewtons. And the modular elasticity of design of a compression member, okay, this means the fifth percentile of the wood and all that. They do this by test to see what that value is. Don't worry about that. I will give you this value for whatever problem you need to do. And if ever you have different species, well, you can just go online. You know, if you go online, what's the EO5 for whatever, and they'll give you the value. You'll find, or if you want to spend the money, buy the handbook. It's all in the handbook. I is a moment of inertia, okay? The effective length factor, of course, in our case, is going to be 1 because we always want to be pinned, okay? And it's going to be 1. And L, of course, the unsupported length in the direction of the applied bending moment. So that's important to remember, okay? How the bending moment is being applied, that's the L, okay? So now, what we'll do is we'll apply this, okay, to a problem, okay? Design the top chord of a residential roof truss for the following conditions, okay? So now the factored axial compression force, so this is your PF force, is 30 kilonewtons, okay? So what this means is that you have a roof truss here, okay? You have a roof truss here. The analysis was done, and it's probably a continuous member here, okay? So they found that the axial force in here, in other words, in compression, is 30 kilonewtons. And most likely, then there's going to be some bending moment here. Somebody calculated the bending moment and found that the factored bending moment was 1.2 kilonewton meter. Okay. The truss spacing is 600 millimeters on center, which is the typical spacing for roof trusses, guys. 2 feet is the typical spacing for roof trusses in Quebec. You can go less than 2 feet, but you shouldn't go over 2 feet. And like I said, 2 feet is a typical spacing. Fully laterally supported by the roof sheeting. Oh, that's good to know. Okay, so I have, everybody understand what this means? In other words, here's a top chord like this, and I have some roof sheeting here, and it's nailed and it's laterally supporting the top chord completely, okay? So this is good to know that the roofing is going to laterally support the compression member. Now, I know you guys have a hard time seeing this, but just because this is at an angle, and if this is straight here, and I have some sheeting here, okay, Well, what's nice about this is that this condition is the same as that condition. Therefore, the PR here is the same as the PR here. And I know I got tables to go find the PR here in the book. This is an exterior wall, okay, with sheeting. And that's what's nice about that. So, you know, it's not the angle that determines, it's the conditions that the wood is, you know, in and how it's being supported and all that, that determines the PR value. And it's a case 2 system. In other words, that's great. So in other words, I have an MR value for a case 2 system now, no longer just a case 1, because the sheeting is going to be able to create a case 2 system for my MR, which is great to know. And unsupported length between panel points is 2.4 meters. So in other words, it would be, you know, the L is 2.4 meters, which is not very long, but it's nice to know. Now I'm going to use SPF number 1, number 2 with an E05 of 6,000. So for SPF number 1, number 2, I got the E05 in the handbook. It's 6,500 MPa. Okay, that's the standard value for an SPF number 1, number 2. And don't worry, I will, if any problems, if I give you an SPF number 3, I will give you the EOI value for that also. And so here we go. So here's our, yes.
I have a question. Like it's halfway related. It's like because we learned something in inspection that the trusses have uplift. Sometimes they because of different temperature. So I'm just curious. Do they take like do we have to take into account this kind of like thing, or you don't know what I'm talking about?
I know exactly what you're talking about, but I can tell you right now. Okay, what you're saying is like you're talking to me about uplift caused by temperature changes, right?
Yeah, exactly. Of what's it called? Of the truss. Like
okay.
yeah.
Well, I can tell you right now, Omar. Okay. Okay. What time is it now?
3:48.
Okay, so at the end of the lecture, okay, at the end of the lecture and at the end of the lab, okay,
Okay.
if all of you that are interested, I will explain to you everything that Omar is asking me, and what he's saying is absolutely wrong. Okay.
I did not say. No, wait.
No,
I did
no,
not
no.
say
What I'm saying by
anything yet.
you're absolutely wrong is that the uplift, or you're talking about because when you're talking about uplift, are you talking about the whole truss going off the roof or just part of it?
Okay, so I think
Because you have to, you know, Omar, you're throwing at me like a glossary, okay? So for example, okay, we'll talk about this. What I'm saying by uplift,
I'll prepare the question right. I'll prepare the question right.
well,
Just
prepare. No, you can ask me. You can ask me how are the trusses affected, and I'll tell you all the situation how the truss could be affected by the condition that they're in. You understand? But when you're telling me that the truss is going to be affected by temperature change, okay, I can tell you that it's
okay,
not temperature change that really affects the truss. It's moisture change.
Okay.
Okay, not temperature, moisture. Okay. And I can tell you that, anyways, we'll talk about that, okay, if you want. But
okay, we'll talk about that for sure.
okay, I mean, like there is temperature, you know, like there is, but the real culprit with wood when there's problems with the truss is the moisture change, not the temperature change. Okay. And then I'll explain to you what happens in that case. Okay.
Okay. Yeah.
So, but okay. Okay, so here we go. Now, in this problem, well, it's very simple, right? I've got this. That's that. I got this. That's that. All I need to do is calculate this, and calculate this, right? Now, here, like I said, I have a, so how do I find my PR value? Now, if I want, I can go ahead and use the formula phi C F C blah, 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 okay? Or since I realize that this truss is being supported by the wood and everything else, it's just like an exterior wall, okay, with the sheeting, and therefore, instead of me going through the trouble of calculating with the formula, okay, let's talk about. First of all, you have to start out by a trial section. In other words, am I going to use a 2x4 or a 2x6? I'll try a 2x6. Okay, that's number one. So you try one, and then the closer you are to one with this trial section, the more the more optimized your solution is. So I'm going to try a 38 by 140. Now, PF. Is there any reason why I cannot use the stud wall tables? No. Why? Because if I go through the checklist of the stud wall table, it says, is low duration standard? Yes. Is it dry? Yes. Is it untreated? Yes. Is the weak axis laterally supported and prevented from buckling about a weak axis? Yes. Everything is yes. So you answer all the questions. So I can go to the stud wall table, even though because it's a compression member. So I will come here with a length of 2 by, what is it? 2.4 meter. So I will go there. So I said I was going to be using 38 by 140, and I said I'm going to be using, okay, so therefore 2 by 4, a length of 2 by 4. I said I'm going to use number 1, number 2, a 2 by 6. Therefore, my PR value is 48.5. Isn't that fast? Because if you understand that even though it's a roof truss, it's a compression member, the sheeting on the roof acts like the sheeting on the wall, on the exterior wall. The weak axis is laterally supported, blah, blah, blah. I can go, and I look at my checklist, I answered yes. There's no reason why I can't get the PR value straight from the table, okay? So that's one thing that if you understand how these tables work, it can greatly simplify your life. If you don't realize you can use the tables, then you'd have to use the whole PR, phi, C, A, KZC, blah, blah, blah. You understand? KCC, and find your PR value through that. But here, because you've answered yes to all the questions in the checklist, we can use the table. So therefore, I get my PR value in kilonewtons right away. So from the table, I get a PR value. Now, this is nice because I need to keep a certain amount of resistance for the moment, because if I, this ratio and that ratio squared and all of this has to be less than 1. So if this is very, very close, it doesn't give me very much to compensate for this situation. So right now I got my PR value. Where do I get my MR value? Or how do I calculate my MR value?
Can I use the PR value?
The TR? No, this is MR. Big difference between MR and
No, the
TR.
PR value.
You cannot use a TR value because you have to use MR.
The PR.
Why do you want to use the PR for MR?
I don't know. Like
I think we have to use the MF.
Oh, we don't have to. Of course, we have to use the MF in the numerator for sure to find the ratio. But how do I find the value of MR?
That's a good question.
It's a good question, huh? So here's my top chord, right? Here's my top chord, and is subjected to a bending moment, MF, right? And I want to know what the MR value is for this member.
Sir,
Yes.
wasn't there a formula before that you showed? Because I don't have the lecture, so I can't. But wasn't there a formula before that showed that can help you calculate the bending moment?
Oh, if you want, yeah, you can. Like the same, there's a formula to calculate your PR value. So the PR is equal to phi FC KZD KC. Remember that formula?
Yeah.
Well, you have an MR value is equal to phi FB, what is it? S section modulus by the, anyways, there's a formula, yeah. But that formula there were tables where that formula gave you all the values for a 2x4, a 2x6, a 2x8, and a 2x10. What table was that? Interesting, right?
I can tell you. Wait. It's the joist selection table.
Exactly, guys. The joist selection table. It gives you MR values. So if now, here I'm telling you that you have sheeting that's at least 3/8 of an inch thick. In other words, 9.5 millimeters. It's nailed at least at every 12 inches, every 300. You have a case 2 system because of the way it's going to be nailed. Wow. Just because it's a top chord of a truss, it's got an MR value. It doesn't matter whether it's being used as a truss member, as a joist, or as a whatever else you want to use it. It's got an MR value. So you go to the joist tables and you find your MR value. So here I come here and I look. So I know that I happen to have SPF, okay? And I'm in SPF number 1, number 2, right? SPF number 1, number 2. I have a 38 by 140. Do I have is it a single member? Is it a case 1 or a case 2? Well, if I know I'm going to have sheeting, I know it's going to be nailed properly. Well, I know it's going to be a case 2. There's my MR value. Otherwise, use the formulas, guys. It's up to you. Now, because of the sheeting that's on the roof, and because it's going to be nailed at least no further than 300 millimeters on the intermediate supports and 150 millimeters along the edges, I'm allowed to take this value of MR from the table. It doesn't matter if it's you understand? It's MR. It's the resistance of the wood. Where it's being placed and how it's being forced into bending, that doesn't change. The MR stays the same. So here I have my MR value of 2.58, and that's where I get my MR value. So from the joist table, I get the MR value of 2.58. So I found this one and I found this one right away. Why? Because I realized that the way that the wood is being supported, the way that the wood is going to be nailed and everything else, I can go to the tables and get the resistance of that size of lumber. Now, of course, what I don't have is the PE value, which I need to calculate, but I've got the formula for it. So the PE is pi squared EO5, and this way I get I. Now, if you guys remember, what's I? Well, this is a 38 by 140, and if you guys remember, the moment of inertia of a rectangle and it's bending about that, so therefore it's 1/12 the base, which is this is B here, times the height of 140, or D. Okay, we'll call it D cubed, and that's the moment of inertia. Okay. So now, this is given to you. This you get straight out of the tables, and don't worry about it. I'll give you all the values for the different species and different grades. And of course, the moment of inertia is 1/12 the base times the height cubed. That you need to calculate. Okay. And KE, of course. Now, what you can do for KE. Now look at this. Okay. Here's the member, and it's continuous at its panel point. So it's almost as if it's fixed here. So if I can consider this fixed and pinned here, okay, I can take advantage of the K no longer being able to, like fixed pinned, I can take advantage of the K equal to 0.8 in this case, okay, if I want. Otherwise, I would use 1, but it's up to you. So here I'm using 0.8 because at the panel point, the member is continuous, so it's fixed, and at the other points, it's probably pinned. So to be conservative, I'm going to use 0.8. But if I'm not sure, I'm going to use 1.0. I'm going to be that much safer. But here I'm taking advantage of the fact that I have a fixed pinned condition. And if you remember from the KE values, the recommended value for wood is 0.8. And of course, the L is 2.4, 8 meters, which is, I'm sorry, 8 feet, 8 meters, 2.4, which is about 8 feet. And of course, put everything into the equation, and of course, multiply by 10 to the minus 3 because this is in newtons. You want to bring it to kilonewtons, and you get 151.4. So that's your the buckling resistance of the column. And therefore, now that I got all the values, I simply put everything into this equation. And hopefully if it ends up being less than 1, it's good. If not, I have to change the size of the member, or I got to do something. So basically 30 over 40.5 squared, 1.2 to MF over MR, 1 over 30, 1 over 30, and so on. And if I do this, here I get 383 plus 580 gives me 9. The closer I am to 1, the more optimum my choice is, okay? I am less than 1, I'm okay. Now, if you happen to use 1 in here instead of 0.8, you can check it. If it still ends up being less than 1, you're still okay. You're even being more conservative. So that's what this means. So when the sun,
sir?
yes.
Sorry, I have a question. If we choose a beam and then, for example, our number is, I don't know, 0.8, but if we chose another beam, our answer will be 0.963. Would you still give us wrong if we use the 0.8? Or
No, no. What I'm getting at is that, first of all, in real life, if I'm doing this interaction equation, okay, and I like, for example, when I was giving you the okay, you'll see this when we do the exterior columns, okay, in steel. Like this interaction equation is like, Gordon, what you have to understand is that let's say I chose a 2x6, okay, fair enough. And all of a sudden I get here, the sum of these two ratios, I end up getting 0.43, less than 1, okay. There's a very good chance that I can get away with a 2x4, so I'll check it with a 2x4. You follow?
You can get away. Yeah.
Okay, so what I'm saying is that the further I am from 1, okay, the safer the member is. The closer I am to 1, the more optimum my design is. In other words, the member cannot be any smaller than that.
Okay, thank you.
You understand?
Yeah, I understand now.
So in other words, like if you chose a member and you get 0.8, I'd live with that. I wouldn't try to optimize it. But if I would get something like 0.5, I would try to see if I can optimize it.
All right, thank you.
You see what I'm saying? Okay, at 0.8, I would live with that. Because especially like when you jump from a 2x4 to a 2x6, it can be significant. You understand? Because these are, you know. So what I'm saying is that in real life, all you're looking for is to make sure when you take one ratio and the other ratio, always the only thing I can tell you, make sure you're less than 1. And the further you are away from 1, in other words, if you happen to be at 0.21 here, then you know you got lots of room to go and try to find something smaller, understand? And what you have to keep in mind is that, see here, for example, here, this ratio here, right, squared gave me 0.383, okay? And therefore it gave me a lot of flexibility to account for the bending moment, and thank God, because this happened to be 0.58 here, okay? So, okay, so that's, I think it was Alex that was asking me, how do you calculate, you know, members that are subjected to bending and an axial force? Well, Alex, this is it, okay? So if you can calculate the axial force, and if you can calculate the bending moment that the axial force is creating, okay, then, you know, and if you're asking me, like, for example, when you have an eccentrically loaded column, okay, when you have an eccentrically loaded column, it's very simple, okay? So for example, this is my column here, okay? And this is the centroid here, and you have an eccentrically loaded column. This is the eccentricity, right? Okay, so the bending moment caused by this is simply equal to P times E. That's it. And that's your moment caused by the eccentricity of force times the distance. This is, you understand? And now I know my MF, and therefore I gotta go and then I go and calculate my MR. So that's how you solve these problems. But this is the equation right here. Okay, so that's for members in compression. Like I said, the PR and the MR values are easy to find when it's a roof truss, okay? So now, Now design the bottom chord of a residential roof truss for the following conditions. So now you got the bottom chord. You got an axial compression tensile force of 13.4 kilonewtons. You got a bending moment of 0.51 kilonewtons. You have truss space at 600 millimeters on center. Using SPF number 1, number 2, because that's if you're going to be using SPF number 1, number 2, you might as well use the same grade for the whole truss members, unless you want to go to something cheaper. And now I'm going to try a 38 by 89. I'm going to try a 2x4, see if it works, because these things are by trial and error. Like it's by trial and error. In other words, you try one. If it works, you're happy. If it doesn't work, well, it's an error. Change size. So now TF is for, okay, so I go to tension members and I said I'm going to be using SPF number 1, number 2, okay, and I'm going to go to tension members to get my TR value. I know I'm not putting any holes in my thing, so I don't have to worry about it. So SPF 38 by 140, and we said we're going to be using number 1, number 2, so therefore here's my TR value. So I get my TR value right away. And then trusses, even those truss plates, they don't remove any area. So therefore you don't have to worry about your net area in this case, okay? So therefore I can use the TR value straight from the table because I'm not removing anything. I have 25.1. And in addition, what I can do, not only can I use that, but I know that I happen to have a case 1 system, not a case 2 because I don't have the plywood, but I have a case 1 system. Therefore, I can take the values in the table and multiply by my KH of 1.1, and I can increase my TR value for that tension member. Okay, so that's something I can do. So TR, okay. So that's one thing I can do for that tension member. And then I have my MF. Now, where do I get the MR value for the 2x4? Same thing. I go to the joist tables, and you'll notice that the joist table starts at a 2x4. Okay, so we have the joist tables. We have SPF number 1, number 2. Okay, SPF number 1, number 2. I'm sorry, that's number 1, number 2, and we have 38 by 89. Now, the difference is that I don't have sheeting. I can't create a case 2. I do have a single member for the MR, but here it says it, that for case 1 systems, multiply MR and VR by 1.1, because in other words, that's the KH value, okay? So therefore, whatever MR value I have here, I'm allowed to increase it by 10%, multiplied by 1.1. I'll take advantage of that. And so the joist table, 0.96 times 1.1, 0.997. That's pretty close, huh? It's not bad. It gives me an extra 10%, better than a kick in the head. So now, here's the interaction equation, okay? So I simply have TF, which is what's given to me. And of course, this you get from your analysis. TR we got from the table, which we just calculated to be this. The MF we got from our analysis. And the MR we got from the table. And therefore, we simply put everything in. Oh, wow, we're at 0.997, less than 1. We're okay. So that means that 2x4 SPF number 1, number 2 would be sufficient to resist the forces that it's being subjected to. And this is what we're going to be doing we're going to be doing these calculations for our project. And the only difference is that we are going to go and calculate what the axial forces are, what the tensile forces are, what the compression, what the bending moments are. And of course, that's where ADA is going to help us simplify our life. And I believe that's it for the lecture. I'm not sure. Yeah. Now, guys, there's no assignments on this. The only thing that this is going to help you with is on your project. So I'm going to stop sharing this. Hold on a second. I want to end the show, and at the same time, I want to close it. So it's 4:10. Okay, so we're doing pretty good. It's like, you guys, is there any questions before I close the PowerPoint on this lecture? Now's the time. I can go back because I'm going to close it completely. And no questions? Okay. Now, what we're going to do is, of course, we're going to, before I get to the lab, Brandon, are you there?
Yeah, I'm here.
Did you get that information that we can work on that thing?
Yeah.
Okay, great. So before we answer Omar's question, we'll answer your question. How's that? And then we'll answer Omar's question, because I promised you that the next lab will work on your thing, okay? So after we finish this lab, guys, for you that are interested, Brandon's got a little problem where he wants to remove a column and he wants to see what he has to do in order to modify the structure by removing a column. And removing a column, guys, is, doable, but you got to know what you're doing. So we are going to do, oops, sorry, I want to go here. Okay, now I'm going to take this. Okay, so here we go. Like I said, guys, I don't think you're going to be getting this PowerPoint, but you might as well, write down what you need to do. Okay, so here we go. We're going to be doing the truss analysis. And then, of course, once we do the truss analysis, we'll have all our forces. We'll have our PF, we'll have our MF, we'll have our TF, we'll have our MF, we'll have all our, our C, our, CF and TF and all that. And you'll be able to design all the truss members based on what you know so far, okay? So here is the truss, okay? Now, the way that the truss is modeled, okay, is, okay, write this down, guys, because you're gonna need to do this with ADA, okay? So write this down. The top chord is a continuous member and pin connected at the ridges. Okay, so where's the annotate? Okay, so guys, so this member is continuous. In other words, this is one member, this is another member, this is another member, but it's all continuous. In other words, this and this is plus, 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 plus. The only place it's released is here, here, and here. I know you guys have this habit of releasing it all over. You do not have to release it there. As long as it's released there, there, and there, you don't have to release it there. It's been released all over. So that's the top chord, okay? Now here you have, what you can do is you can put a pin support, and here you put a roller, okay? That's the most conservative way of analyzing this, okay? So that's basically, okay, so the top member is pin connected at the ridge. And the bottom chord is continuous at the panel point and pin connected at the center of midspan. So in other words, this member here, it's pin connected here, continuous, and pin connected to this member. You notice I don't have two circles. I know that, don't do that. It's some programs will crash on you if you pin. Thank God ADA can get rid of that redundancy, but don't do that. You just have to release it on one side and it's pin connected. Here is continuous and here it's pin connected. Okay, so you have to make sure there's a plus sign here and that there's a circle on that side. There's a plus plus on this one, and then there's a plus and a circle on this side, okay? Now, the web members, this is a web member, that's a web member, that's a web member. These are pinned at both ends. That's how they're actually, because they're, you're just going to, they can be fixed or they're pinned. So the web members are pin connected at the top and bottom chord, okay? Now, I do suggest, okay, preliminary member sizes, okay? Make the top chord, all the top chord 38 by 140, okay? And of course you can use, in the bottom, make all the other members 38 by 89, in other words, 2 by 6 and a 2 by the rest, all the other members. Use SPF number 1, number 2, okay? And if you remember with ADA, there are trusses that you can take. You can model with the Fink roof, the Fink roof truss in ADA with 4 panels. So when you pick the Fink roof truss, you put in the 4 panels, you put in the geometry, you put like the span. What's going to happen in ADA is that you're going to get this. Let me clear this drawing. In ADA, you're only going to get this. Okay, you're going to be getting this here only in ADA. Then once you model this properly, with the right height and everything else, you simply add another node there, add this member there, and add that member there. And that's how you're going to complete your. So you get all of this done by ADA, and then you simply add another node, another member, and you'll complete your truss. So once you've modeled everything, of course, you're going to worry about your loads. Okay, so the loads, first you worry about your model. Now, if you remember, we already calculated these when we did the sizing of the strip footing underneath the house. So it's exactly the same loads here. I'm just going to repeat them. So for the top chord, now here I'm going to separate it because you're going to have loads on the top chord, you're going to have loads on the bottom chord. So since they're going to be different loads on each member, we're going to be putting them separately. So on the top chord, I know I have the asphalt shingles, and I'm going to use the same dead load for the asphalt shingles. And I'm going to use a tar paper. Okay, like I said, normally I wouldn't even include this, but I put this in more for, And then what else do we have? We have the 1/2-inch plywood. Okay, and of course, I don't have to worry about the weight of the member itself because ADA calculates the weight of the member, and therefore I'm going to add 0.2 kPa to the top chord. Okay, now the bottom chord is supporting what? It's supporting the insulation. Okay, and what else is it supporting? Well, the gypsum underneath. So therefore it's supporting the gypsum. So therefore the bottom chord is supporting 0.3 kPa. Okay, now so what that means is that if my roof trusses are spaced at 600 millimeters on center, the tributary width of each truss is 0.6 meters. Therefore my WF is going to be 2 times point, it's going to be, so therefore the tributary width of the spacing of the truss is 0.6 meters. Therefore in ADA I need to put a uniformly distributed load on the member. So I take 0.2 times this, that gives it to me for the top chord, 0.6, that gives it to me for the bottom chord. Okay, now once I've done that, so the superimposed dead load. So in other words, now what you need to know is with ADA, okay, you got to be careful. Okay, if you don't tell the direction, like here, when the members are horizontal, okay, it's not a problem. You don't have to change nothing. ADA will always put it perpendicular or globally this way. Okay, so ADA automatically does this by default, but that's okay for the bottom chord. But here, if the force is actually acting perpendicular to the member here. Okay, so in ADA there's an option here where it says strong axes, and you choose that one, and ADA will put it perpendicular to the member. Okay, and that's how you specify this angle in ADA for the loads. Okay, so that's for the dead load. Now for the snow load, the National Building Code always wants you to apply the snow load globally horizontal. Okay, so globally horizontal for ADA. Okay, for ADA, globally horizontal is going to be, okay. Oh yeah, like I said, note the angle of the load. Okay, if you don't do it this way, ADA is going to be putting it vertically. Okay, so you got to put it strong. And then, so the snow load is 0.6, of course. And this is what ADA is going to do. Like in other words, it's going to be putting globally, and then under the option, you're going to see one option, put global horizontal, and that's how you have to specify the angle for the load. Otherwise, you won't see it this way. And that's how the National Building Code wants you to apply the snow loads to a roof, globally horizontal. If you remember from your structural analysis, when you looked at the snow loads, it was always applied globally horizontal, no matter if the roof is flat or if it's pitched or whatever. If it's, you know, that's how you,
Sure.
yes.
At the bottom chord, you did not connect the beam, or why you still have like see the bottom one? Like let me annotate.
Hold on, let me share,
No, here's this one. What is this?
That's because this member, you cannot have a piece of wood that's 20, whatever it is, 27 feet long.
Yeah. Ah, okay.
So therefore, you're going to have a connection in here. And therefore, this connection is going to be, this member is going to be pin connected to that member. You're not going to be able to fix it. It's wood. You can't weld them. You understand?
Oh, okay. Yeah.
So in order for those two, like, so it's going to be like a pin connection. Okay, so it's going to allow the moment to bend, but it's not going to allow, you know, like, so it's going to be pin connected. You understand?
Yeah.
It's like having a smooth pin here. You understand what I mean?
Yeah, but in that case, does that affect the panels when I choose the number of panels, or
No. This is like, no, the number of panels is going to give you the geometry, and then of course you're going to have to split this member.
Okay.
I mean, if you don't remember how to do it, if you guys want, I can help you with your ADA, but you know, I'd rather you guys stumble with it. I'm giving you everything that you need here, okay? So do you understand what this is, Omar? Because the 2x4.
Yeah, I got it, because last time when we did it on not on wood, we did it with steel, I believe. That's why I thought why you didn't connect the two members. Yeah.
Oh, because with steel, I can easily get a member that's 28 feet long.
Yeah.
Okay. So to do this connection, and as a matter of fact, okay, I did this to simplify your life. I put it right down the middle, okay? But in real life, the connection is always never in the dead center, it's offset a bit, so that when they lift the truss, it doesn't break. You understand? In real life, if ever you go on the site, the connection is here, not there. And the reason why they do that is that if they happen to lift the truss sideways, if it was right in the middle, most likely it would break. Isn't that interesting?
Yeah. Okay.
Okay. But in real life, they put the connection somewhere around here. Okay. So if ever you go look at roof trusses and you look at the bottom chord, you'll see that the truss plate is here somewhere. Okay. Never in the middle. I did this to simplify your life so that you can just split this member in two and put it right in the middle. Easy enough.
Yeah.
Okay, and then after that, if you want to get an idea what it's going to look like, so once you get this all done, of course, your load combinations are going to be very simple. Okay, for your, you know, limits, I should have put ultimate limit states here, but it's 1.25 times your dead load, 1.5 times your live load, and 1.5 your superimposed dead load, and 1.5 times your snow load. And of course, for your service load, once you've checked all your members and if everything works, then you go check your serviceability limit state. You simply run 1 point and see what the deflection would be under the span. And if it happens to be less than L over 360, then you're okay. And that's it. And then of course, what's going to happen, this is what you're going to see, the results. Okay, this is what the axial forces look like. I hate ADA for that, but this is the axial force. In other words, this is for the top chord. This is for the top chord here. In other words, it's got 21 kilonewtons of axial force here, and it goes down to 18 there, and it goes all the way down to 18.7 there. That's for the top chord. And then for the bottom chord, these are the tensions in the bottom chord here. And this, of course, is the axial force in the overhangs, which is peanuts. And so these are the actual, this is going to be the axial forces that you're going to, you know, like, so for example, I have to find where the greatest bending moment is and see what the CF value is, okay? And then after that, the bending moment, well, there you go. So there you go. So this is my MF value. Then I find my axial force here. That becomes my CF value. Here's my MF value for the bottom chord, and then my TF value, the highest one. And then on top of that, I still have to design these members here. This one's in compression. So therefore from AD, I will get the length of this. And then this, I have no choice but to calculate PR is equal to phi, because I have no sheeting, I have nothing, I have no choice. I have to calculate what the PR value, make sure it's greater than the PF value that's in here. And this one's simple. I simply have to make sure that the TR value is greater than the TF value. So this one I have to calculate with the formula, and this one I get straight from the table. So as long as the TR value is greater than the TF value in this member here, and it should be, because here I have it's relatively small. Sorry, this is the bending. See, you have a bit of bend. The only reason why you have a bit of bending moments in these members here is because this is self-weight of the member that's causing this bending moment, but you can neglect it. This is like, it's considered to be 0, okay? 0.01 is 0, so don't worry about that. And that's it, gentlemen, ladies and gentlemen. And hopefully, what time is it now?
4:30, sir.
4:30. So if you guys want to get started, I'm going to be here to help anybody with their ADA problem, or we can go ahead and work on Brandon's. You guys can look at how we treat a problem. Brandon has a very nice little project that we can all look at that would be very interesting for you guys to get an idea of what to do. What do you want to do? Guys, it's your time. You understand?
Sir?
Yes.
I'm just maybe gonna work on it. But just a quick question: the roof truss, the shape, is it the rectangular Prit or the what's it called?
I told you, use a Fink roof truss to model.
Never mind. No.
Use a Fink roof truss to model the roof truss. I gave you the size, the geometry, the dimensions on the project, and you're gonna have to calculate the height and whatever. And you're gonna have to model it. You understand?
Yeah. Okay. Thank you.
Okay. So, okay. So, do you guys want, like, if you guys want, we can work on Brandon's little project so you guys can see how you can handle that in real life, if ever. Or do you got? Pardon?
Yeah, it would be interesting to work on Brandon's project.
You want to see it? So, because I promised him that we can do it in the lab, so you guys can, get an appreciation of what to do if ever you need to do something like that. And then after that, we can talk about Omar's thing, and I can explain to you what happens in the roof truss. Okay, so Brandon, you're gonna have to share. You're gonna have to share with. Hold on a second. I have to stop sharing, and I'm gonna have to give you the chance. Multiple participants. Yeah. Okay. So go ahead.
Well, basically it's, we currently have 2 columns in our basement holding up our beam.
Yeah, but Brandon, you're gonna have to start drawing it so that we can take a look at what we're looking at. So,
okay.
Like take your whiteboard, share it with everybody, and then we'll be able to. And then I'm gonna ask you to. Well, I might even ask you for some remote. I might want to intervene, so you can give me authorization to. Okay.
Yeah. So currently we have like the exterior wall here.
Yeah, Brandon, you should have started. You should have started with the drawing that you had last week. Remember, you showed me a drawing with Rivet. Okay. Now this.
Yeah, well, I can do that. Just have it. I'm loading up VMware, so it'll take a bit for me to log in.
Okay, not a problem. So in other words, this is a plan view of what? Of your basement, first floor?
We have another one here. And then, yeah, so we just want to remove one and end up having just that one in the middle.
Okay, so this is an elevation, right?
Yeah.
Okay, so this is the elevation. In other words, this is how, so I'm assuming, hold on a second. Do I have, okay, I can annotate, right? I can annotate. Okay, so basically what you're saying is that you have, there's a beam here, right? And so do you know the dimensions of, like, so do you know how this beam is being loaded?
Yeah.
Okay, go ahead. So you have to show me the forces that are on the beam.
Oh, there's nothing, there's no load bearing walls on top of it. It's just support.
Okay. Go ahead. Well, what I'm
Okay.
saying, Brandon, like Brandon, let me tell you what, like if you're asking me what to do, okay? So you have to come up with what we call a load diagram, okay? So in other words, you have to determine, like now I'll just explain to you what you have to do, and then you'll okay. So you have to determine what is the load that this beam is carrying. Now it can be a distributed load, it can be a distributed load with a constant load. It doesn't matter what you have as long as, okay, so I just want to, okay, so basically, like if you tell me it's got just one load here, okay, you have to determine that. And then how do you determine that? Well, you find out what is it supporting, you find what the tributary width is of this beam, and then you multiply by the tributary width and you've got your load. And of course, you're gonna have to factor those loads and you have to determine your WF, okay? So for example, if there's floor joists that are going this way, well, it's simple. You calculate the dead load of your floor, and then you know that it's 1.9 kPa for your live load, and there and so on and so on, and then this is the tributary width, so this is your WF. So, and now that's number one. Now if you want to remove this column here, which one do you want to remove? Brandon?
Move it over the.
So which column do you want to remove?
Okay, what's it? It's like this column that we remove.
Okay. Now, do you know the composition of the existing beam?
Yes. Hang on a second. It's a 4-ply 2x8.
A 4-ply?
Yeah.
It's a 4-ply, and what is it? 2x10s?
Uh, 2x8.
Well, look, Brandon, it doesn't matter. I'm just going to give you the steps to going in and
Sir,
out.
I think your internet's cutting out.
Yeah, it's cutting in and out. It's at least it's reconnecting me right away. Understand? Like I'm having problems with my internet right now. Okay, so Brandon, look, like just to let you know, like I was hoping you would have everything, but look, most and do you know, for example, anyways, look, I can guarantee you, that if you remove a column here, okay, this is going to be no longer any good, okay, guaranteed, okay. So what you're going to have to do is, like, for example, if you know your loads, if you can calculate your loads correctly and get this accurately here, okay, then what you can do is you can calculate what your MF value is in here, okay. You can calculate your MF value in here. And then of course, you're going to see that that MF value is going to be greater than the MR value for that beam. You're no good, okay? Now, I'll give you options, okay? I'm going to tell you one of the options you can do, okay? One of the options you can do, and then we'll do this in the steel class. So if you get all this information, we'll do it in the steel class. So as far as the wood goes, there's not much you can do. I mean, you're not going to start putting 18 plies in here and hopefully you'll be able to span from there to there. I don't think that that's going to be a good solution. One of the typical things that get done when you have a built-up beam in a house, you want to remove one of the columns. One of the typical things that gets done is this. Okay, so here's your built-up beam, like this. Okay, and believe it or not, you guys have all the information to be able to do this on your own. Okay, it might seem, so what happens here is that this is your built-up wooden beam, right? So what you do is you calculate what your MF value is, okay? You find out what your MR value is for this beam as it is here. So you know that the additional MR value that you're gonna need to support your load. So that's gonna be your additional MR. And what we normally do in this case, okay? I just wanna change color so you guys can do it, okay? we take channels and we put channels back to back like this, okay? Okay, we put channels back to back like this. And we can, for example, we can find out what the MR is for one channel. And of course, we know we're going to be putting 2, so we simply multiply by 2, so we know the size of the channels. And then based on your shear flow equations that you learned in physics, okay, where you have the shear flow, which is V, what is it? I forgot the formula, but you should be able to calculate what are the bolts and the spacing of the bolts that you need in there. And what I do strongly recommend that if you're going to do this is that before you do anything here, you jack up the column. Okay, you jack up the column at least 1/8 of an inch above its original position, so that when you put all the steel reinforcement and you release the thing, the wood will then work with the steel together. If you don't do that, it's not going to happen. So one of the mistakes that people make is they don't jack up their column so that the column now is up. So this way, when they put the steel on it, you have to load the column. How do you load the column? Is by jacking it up. And then when you attach the steel to it and you remove that support, the steel and the wood now work together, and it's going to, and of course, we would have to calculate the moment of inertia required and all that. So if you can get all the right information, in other words, if you can get a nice set of drawings showing me how the structure is laid out in your house, we can go through it step by step. You understand? But it's just a question of, without the geometry, I can't do anything. Without, and then from that, without knowing the composition of the assembly, I cannot calculate the loads. And without where these columns, so this is, this is all the stuff we're going to be needing, Brandon, if we want to do this and come to some kind of a solution. Understand? But I'm just telling you, yes, it can be done. And, based on what you learn in physics and what you're learning in my class, in theory, you should have the capacities of doing this on your own. But like I said, I'm telling you this as an academic, not as an engineer. You understand? And I'm going to give you the steps, and it's going to be up to you to make sure you get all the information, because I can do all these calculations for you, but if you give me one piece of geometry that's wrong, or something that one of the loads that is not properly being carrying through the house and it's actually going on the beam, this is something that so the drawings is the first thing, and then after the drawings, the loads, after loads, the analysis. Once the analysis is done, well, then we can look at what are our options in order of the additional reinforcement. And you might have to reinforce this column here. You might have to reinforce this column here because there's more loads that are going onto that column. So what do you have today in terms of information?
Well, I have the joist lengths, the spacings.
Okay, so let me clear this drawing here. Okay, so so show me what you have so far, and we'll take it from there.
Okay, well.
You have drawings? Okay, no, I want you to put up drawings. I don't want you to draw it. I want you to put up drawings. Do you have your drawings?
Yeah.
Okay, show me your drawings. That's what I want to see.
Yeah, it's loading. Yeah.
Okay, so while Brandon is loading, Omar, we'll go back to your problem while Brandon is loading this problem, okay? Omar, repeat your question. Omar, are you there? I guess he's not there. My internet connection is unstable.
Yeah, I'm there, but like I want you to see the book, sir. I'm there.
Yeah.
Hello?
Yeah, go ahead, Omar. I'm listening.
Sorry.
So go ahead, Omar.
Yeah, you're okay. So the thing is, I want you to see what I'm talking about. I have the book, the PDF version of the book. So I want you to see what I'm talking about.
Okay, so Brandon, we'll come back to you, Brandon. I want to I'll finish off with Omar. So, okay, so Omar, go ahead. Share with me what you have. I want to see what you're talking about.
Here we go.
Yeah, that's not that. So what does it say? You talk about truss uplift, okay? This one here, a phenomenon known as truss uplift is relatively common in cold climates. The temperature and humidity changes. So it's humidity, you understand?
And temperature.
And temperature, but it's not just temperature. You understand? So what happens? What happened was, okay. Well, temperature. The reason why it's also temperature. And did they explain to you what the big culprit is?
I mean, this is the only explanation that
Isn't
we
it
have.
that like it's the bottom core that shrinks so it bends upwards?
No, the culprit here. Okay, the culprit here. What's causing all this problem? Okay, can I ask to annotate?
Yeah.
Okay, first of all, do I have? Can I? This is me, right? Okay.
Yeah, that's
okay. The culprit here, guys. You know what's causing all the problems? This right here. The insulation. Okay. So what's happening is that the insulation is keeping the bottom cord at one temperature, and it's keeping the moisture content at one temperature, and the rest of the roof is undergoing another temperature. And because of that insulation, it's causing the truss to have moisture and temperature changes. And what happens is that when, because of the shrinkage of the top cord, because of moisture changes and of the web members, the thing tends to bow this way. You see that? And it tends to disconnect from the wall, okay? And of course, what they're showing you here, the simple solution to that is to simply put a molding on the wall, so that when the truss, the bottom cord goes up and down, it's just going to accommodate that displacement, and people won't be seeing any unsightly cracks, and everybody's going to be happy. Now, this happens when your trusses start to be relatively long. Okay, in other words, you're looking at about 40 to 50 feet spans. Okay. I haven't seen this occurring very much in a 20, 25 foot span or a 30 span home. Okay, this happens when the spans are relatively long. So if the spans are not extremely long, it's not even an issue. But when you start getting 50 feet spans and you have a wall here, you understand? Because what happens is that when they're building this, here's my bottom cord, here's my wall. Of course, they have the furring strips. They put the gypsum board here. They put the gypsum board here. They do a nice joint in here. Then all of a sudden, this goes up, poof, and you get a nice crack along the top of the wall, and everybody panics. Okay, so structurally, the problem is the insulation that's keeping the bottom cord at a certain moisture content and at a certain temperature, and that's what causes the truss to bow upwards.
Okay, so my question was initially that do we take into, like, do we calculate anything so we can consider these, like, because cracks will occur eventually?
Oh yeah, but what you do is you tell the architect to provide this detail instead of having the crack. You understand? This is what they're showing you here, is that if you don't separate the steeling from the walls and put some kind of a molding here that just covers up the displacement, then you're like, this is the simplest solution. Like when it comes, like, guys, when it comes to nature, like I told you, structural engineers do two things. We either resist the force of nature or we comply with them. And in this case, this solution is simply complying with the force of nature. So when nature wants to contract and expand, contract and expand, we're just letting it go up and down and not a problem. You understand?
Okay.
Do you follow?
Yeah.
So in other words, do I take this into consideration when I'm building a roof truss? Well, depending on the span, okay? Depending on the span, if it starts exceeding 40 feet, I will tell the architect, all your walls that are coming to the underside of my trusses, don't attach them. Give them this detail.
Okay, I see. All right.
Do you understand?
Yeah.
Now, you want to see another problem with wood construction that people don't have? Okay. So this is a typical, like I said, like this has to be, the spans have to be 40, 50 feet. Okay. I personally, I don't think I've ever seen this with trusses that are 30 feet in span. You understand? And most houses have 30 feet spans, because what they do is they'll always try to span the trusses in the short direction of the exterior walls. So that's why this doesn't become an issue. But if all of a sudden, like I've seen, for example, I don't know, the architect had this fantasy of having the slope going this way, and he wanted to support from the back wall to the front wall, and therefore we had, you know, like we start getting into 40 to 50 foot spans, okay? And in those cases, yes, you know, we start getting into the problem of the bowing. You understand? And all they're telling you here is that if you actually go into a house and you see a crack occurring along the top of the wall, right? Because any wall that's going to the underside of these trusses, as soon as the truss bows up, like you can appreciate if my wall is here, not much of a problem because the bowing is very little. It usually happens around the center. You understand? So this is what they're saying. Install 1x6. Install between trusses anchored. Okay. And what they're trying to show you here is that when the drywall, when the drywall, you know, is attached at this corner, of course, it's going to break. Okay. So crack forms at the central ceiling to wall intersection, and that's typical. So that's one situation. I've seen other situations where people don't allow for the shrinkage of the wood, and that's another moisture change. Okay. And the biggest culprit when it comes to shrinkage, believe it or not, are these plates. These plates are the ones that contribute to the most when it comes to the shrinkage of the wood, okay? So what happens is that on average, okay, when I have a bearing wall, and I have a top plate here, a top plate there, and a top plate there, like this is for one floor. Well, most of the shrinkage occurs here, okay, because of the direction of the grain. This thing on the average will shrink about 1/4 of an inch, okay? So it's not too bad when you only have one story. It's not too bad. But when you start building a 3-story building, okay, when you have a 3-story building, okay, all of a sudden the roof goes on your wood structure. And then the bricklayer comes and he starts putting his bricks on the outside. Okay, he starts putting the bricks on the outside here. So I'll do this in red. And all of a sudden he gets to the very underside of this truss here, and all of a sudden he says, "Oh, look how lucky I am. My brick fits perfectly." Okay. So what happens is that when the thing gets built, no problem. In other words, everything is nice. Now all of a sudden I got this brick wall here on the outside that doesn't go under any moisture change. And all of a sudden I've got my roof truss here, and my bearing wall where the roof truss has gone down by 3/4 of an inch. So guess what's going to happen at the ceiling here where the gypsum meets the wall? You're going to get the same problem. It's going to crack. Okay.
Yeah.
So what you have to do then, you have to go outside, remove the last brick, and put the structure back onto the wood. And it's end of story. You see?
Yeah.
So that's another problem that occurs. You understand? And people ask themselves, well, what do we do? Just tell the mason to come back, and you should never have put his last brick there. You understand? You always have to make sure that you have at least a 3/4 inch space between the last brick and where the wood truss is going to be sitting on top of the bricks. You understand?
Okay.
So, I mean, this is interesting. I mean, like the guy that discovered. Because when you were talking to me about uplift, I thought you were talking about the uplift caused by the wind. You understand, Omar? So
Okay.
that's why I wanted to know, like, are we talking about uplift of the truss? You're talking about the bowing of the bottom cord, okay? So this is bad wording. This is really bowing of the. I would call this bowing of the bottom cord, okay? I don't know why they use the word uplift, because for me uplift is the whole thing wants to go up. You understand? It wants to go up here, it wants to go up here, it wants to go up there. That's uplift. This to me is bowing. You understand? So a phenomenon known as truss uplift is relatively common in cold weather. The temperature and humidity changes in the attic during the and believe it or not, it's mostly the humidity. Okay. So in the attic, affecting the section of the truss above the it's above the insulation level. So this is the culprit. As we insulate more and more our roof spaces, in other words, as this bottom cord becomes more and more, embedded in that insulation, okay, the more that these effects occur. You understand? Expansion in cold weather and shrinkage in warm weather. Okay. So there you go. So that's it. Now,
All right.
if you want, Omar, I mean, I think with ADA, I'm sure that I think ADA allows you to do temperature changes in their analysis. Okay. But what the ADA temperature analysis does is not for this type of situation. It's more for, like, for example, if I happen to have a column here, okay, and this is my exterior wall here, okay, and this column goes from outside to inside. So this here is another situation where you would actually do a temperature into your calculations, because in the winter when this is minus 40 and this is plus 20 or 22 because of the heating inside the building, well, this is going to cause a lot of temperature stress on your column. So and ADA can do this analysis for you. You understand? So in that case, yeah.
Yeah.
You understand?
Well, thank
But
you.
this is, like I said, the culprit is this guy here. It's the architects that are over insulating our it's not their fault. It's part of the law, the energy conservation law. Okay. And that's what that is. And like I said, it's surprising that like here they don't give you an idea of like when does the problem really occur. You understand? It's like if I have a very small house, like in other words 25 feet, unless there's a super big change, you know, I've never really seen the problem in a shorter spans. I've always seen the problem when we're talking about longer spans. You understand? So okay, sounds good. So thank you for bringing that up. So let's go back to the drawing. Mr. Brandon?
Sorry, sir.
Yes.
I just have 2 seconds. Because I'm doing the trusses on ADE right now.
Okay, show me your file. Share your file so that we can look at it together.
Screen 2. Can you see it, sir?
Yeah.
I just have a question. For the material here, which one do we choose?
SPF.
Is it visual though, or level?
In other words, here, look, go, can you share? Let me, give me the request remote control. Okay, so you go, this is me, right?
Yeah.
This is SPF number 1, number 2. This is the one you choose, okay?
Oh, okay.
That's the one, and make sure it's dead. And that, in other words, SPF number 1, number 2, that's how they say it in visual. Okay, this is visual, and SPF number 1, number 2. And that's the right size, 38 by 89. Sounds good? And that's for your bottom chord, right?
My web member. Yeah, exactly. My web.
All your web members and your bottom chord are all this.
Yeah.
Perfect. That's
can you just double check my end supports if I put them correctly?
Well, this is good. This is roller. This is pin. That's good. And this member here. Oh, hold on a second. Let's. Like, what you should do is you should always, when you're doing this, it's good to see things on the thing. Okay. Do you like to see lengths?
Yeah, sure.
I mean, that would help. Sometimes it would help. Do you want to see your? Let's look at the.
Yeah, I didn't put all my material yet, though.
No, it doesn't matter. Well, that's what's good about it. Like material, this way it reminds you what you've done and what you haven't done so far, right? So, hold on a second. So, so you're gonna have to split this member.
Yeah.
Okay, that you're gonna have to split. Do you remember how to do that right here?
Yeah.
Okay.
Well, once I watch the video that we've done a year ago, like it's gonna bring back a lot of stuff that we did. So.
No, but here, like you see this split. Okay.
Yeah.
Okay, so that's where you can split the member. If you, okay, so you just like you pick this. So in other words, how come these members are not the same? Adriano, hold on a second. You're gonna have to do something. Hold on. This is the Fink truss, right? Okay.
Yeah.
Okay. Let me go get the
That's the problem I had. I had some problems. Can you check? Yeah, please.
Yeah, hold on, like guys, like that's why we're all here to learn. Okay, don't worry about it. I want to like I'm looking at the project. I want to see the truss, the geometry of the truss. I have to go look at the geometry truss. Okay. Okay. I'll tell you what you okay, hold on. I think there's the truss. Okay. Adriano, number one. Okay, if you're working imperial, okay. Number one, if you're working imperial, you should work in imperial. You understand? So imperial shapes and imperial, you understand? That's number one.
Okay. I put everything in the tree.
No, the reason why you want imperial is because if I look at this, okay, here I have 8.6 feet. This is not right. The shape is right, but the dimensions aren't right.
Okay.
You follow? So for example, the easiest way to correct this is what you do. Now, not because this is just to help you model it as quickly as possible. You understand? Like before you go to your members, okay, before you go to your members, you should always make sure that your model is complete, okay? So right now, what you want to do is like, I'm going to remove, okay, let me show you what I'm going to do, okay? I'm going to remove this, I'm going to remove this, I'm going to remove this, okay? Fair enough? Now, you see here where it says nodes and support. I want the numbers, okay? Apply. This is node number 2 and that's node number 6. Fair enough? Okay.
Yeah.
So I'm going to go to my structures. I'm going to go to my nodes. And node number 2, okay, it's really at 9 feet 3. Okay, so it's really at 9.25. I'm sorry, I'm going to correct this. You understand? So this is how you correct it. You understand? You just come here and you correct your nodes, 9.25. Okay. For some reason, it's not. Can you put that value in?
Yeah, I'll try.
Okay, so put 9.25 there. So 9.25 times 2. And then this one here would be at node number 6. It would be at 18.5.
Okay.
Okay. Now, as far as the height goes, I'm not sure. First of all, well, it's 9.25 times. Well, I can't did you put the right height? 9.25 times 3.
I think your height is a little low. I think.
Well, 9.25 times 3 divided by 4. What did you get as a height, Omar?
I got 1 second. Let me do this. I got like 13.88.
No, that's too high.
That's too high.
Yeah.
Sure, I had gotten 4.2 meters. Well, 2 feet you have to convert it there, but.
Well, why did you convert it when you can work in Imperial?
Yeah, I was working with my drawing, my sketch that I did in my book. I forgot to check the.
This is good. 6.94 is good. I know that's correct. Okay? So you did it right. Okay. This is good. I just did the quick calculation. I took 27 feet 9 inches and I divided by 4, and that's what you're supposed to get. Now, why do I divide by 4? Because I take half the span, and it's 6 and 12 is half of that, so I divide by 4. So I got, as a matter of fact, I got 6.9375. So 6.94 is perfect. So press OK. Press OK. And now let's go back here. You see? And we go back to lengths. Can you, like, I think it's better if you, okay. Now you see, here's the length of your compression member. Now, if you don't want to convert it, go back to metric now, and you can get this length. When you're going to be designing this member here, you don't have to calculate the length. You get it off ADA. You understand?
Okay.
Now,
is it okay if the bottom right one is like 1 decimal off? Sorry? The bottom right member, it's 9.26 instead of 9.25. Is that okay?
Can you use your pointer to point at what you're talking about?
Right here.
I can't see it.
The 9.26 on the bottom right chord. This one here.
Oh, okay. So in other words,
A point one off. Is that okay?
It won't hurt, but you can go and change that if you want. You understand?
Okay, that's true. Yeah, with the way we just did. Yeah. You're right.
Like in other words, like you take, what is it, 9.25 times 3. So it's supposed to be at 27.75. What node was that? Go to node number 7. Go back to structures. And just change that to 27.75 if you want. You understand? Because it's probably the conversion. You understand? And press OK.
Okay, there you go.
You like that, right? Guys, remember, these are spreadsheets. You can modify. Now, Adriano, you're going to have to add a node here. Okay.
In the middle?
No, here, because you need to extend this. You need to add a node here. See where I'm pointing here?
Yeah.
And you have to add a node there, and then you have to add a member, and then you're going to have to split this one. Okay.
Yep.
And then once, like in other words, first worry about doing your geometry, then assigning your members, assigning your material, making sure that the end conditions are good. Okay. So for example, when you're ready to assign the material, what I would do is I would take this one here, right? This one, and because I can't seem to pick, okay. So, you know, you pick my, okay,
you control and you press them all.
pick this one, pick that one, pick that one. And then when I go for, properties, okay. And then this way, when I'm going to be pinning them all, I come here and I do this, you understand? Now I know I've got that all pinned, and then I go and assign the material, you understand?
Then the property, yeah.
You understand? Timber,
rectangular round.
Rectangular, that's it. Rectangular. No, I'm sorry.
The first one.
Yeah, the first one. That's it. So this is a 2-inch, right?
Yeah, it was
2 by 4. Okay, they even go down to 2 by 2, right? 2 by 4. Okay, and of course the material, timber, visual grade, SPF, visual grade SPF number 1, number 2. And of course you want the thing to calculate the self-weight, so you put that there, and it should be okay. Now, of course, like Adriano, to make sure, okay, like I said, to make sure always we're here, attributes, look at your end conditions. So, these are like, I use my visual graphics a lot to make sure I don't forget something, so here, oh, look, it's all nice, you understand? Once I know that my lengths are all good, like before I would even do this, like I said, go add your node, add your member, okay? Because you know that this node here is at minus 1.5 down by what is it, like it's a slope of 6 to 12, so therefore that would be minus 1.5 one way and half of minus 1.5 minus 0.75. You understand? So you go to your nodes, go to structures, go to nodes, right? So you add a node, you add another node, right? And of course these are normal. So here the x is minus 1.5.
Wait, how do you know it's 1.5?
Because it says it on the sketch, 1 foot 6 inches. That's 1.5 feet in the x direction.
I have to go look at that. Yeah.
Guys, you don't work like this is what I'm saying. You guys rush to the program. No, you got to do your calculation. So this way you know what to put into ADA. You understand? You follow what I'm saying?
Yeah, I do.
Okay, so put minus 1.5 now for that, for the x, because like I said, from my, okay, that's for, and the y, you're going to go down. So you're going 6 and 12. What's half of 1.5? So minus 0.75.
And then
that one is, well, it's 27, it's 27.75 plus 1.5. So 27.75 plus 1.5, that's 29.25. And of course, it's still minus 0.75 in the y.
Sorry, repeat that?
Well, the y is the same. The y
Oh, yeah,
coordinate
true.
it's
Yeah.
got to be the same.
Minus 0.75. It's on the same. Oh,
Well, you have to add another node in the middle of the bottom chord.
No, you're going to split the member and the program's going to add it automatically. You understand?
Okay.
oh, why didn't that work?
Because you didn't put the right value. I saw you made a mistake. I wasn't going to say anything. Because look, you put a 0.
Wait.
It's supposed to be 27, sorry. 9.25 times 3 equals 27.75 plus 1.5. It's supposed to be a 29.25. Why'd you put a negative sign for? I don't understand why you put a negative sign.
Oh, okay. Yeah, I thought it was negative as in the seam. Okay. There you go.
You're going
Yeah,
from the
it's true.
origin, you're going to, why did you put a negative sign? There you go. Now you got your two nodes, you just add the members, understand? Okay, so you guys don't like
Oh,
to
wait,
take,
no.
you guys should take off those pop-ups, you know, like, I don't know.
Like this, as this pops up right away?
No, yeah, exactly. What you do is like, even before you start anything with ADA, you come to project configuration, you go to file, project configuration, and you remove these. So this way they don't pop up in your face. You understand? You undo those, apply, okay? So now when you want to do something, the program won't do that anymore. You control when you want those pop-ups, you understand? So go add the other one, because as soon as you add the member, it kind of adds you the right, if you know, there you go. And there you have it. Now all you gotta do is go split this member here. So pick the member first, and then go here, split.
Oh, wait. Yeah.
No, just split it. Put don't worry about it. And then you're gonna go adjust the node. You don't have to worry about it.
I don't have to write, what do you mean, sir? I don't have to write the distance between the doors?
Yeah, you have to specify, but don't be accurate.
Okay.
You know what I'm saying is
Oh,
that
okay, I get what you mean. So because you're gonna adjust it later.
I can adjust it after by adjusting the node. You understand?
Put it now. All right, and then I have to pin it on one side. And then it's gonna be. Oh no! Whoa.
What happened there? No, it's MX, not MY.
It should be this one, no?
It depends. It depends on your I and your J. I don't know. Pick one, and if it's not, it's going to be the other one. So.
No, no.
Anyways.
I'll figure it out.
No, you're on the right track. But what I'm saying is that now, look, this is node number 8. I'm sorry. Where's your? What node is this? How come
this is 2, this is 8, and this is 6.
Something's wrong. Hold on a second. Hold on.
These have the same number node.
Something's wrong.
That's exactly what I got at the same time.
Okay.
And then your real fly. They both give you number 8.
Something's wrong. So that means that you've assigned the same node number. That means you're going to run your analysis. You're going to get a big mistake. You understand? You're going to get a big mistake. So go to structures, go to nodes. Yeah. Okay.
Yeah, they're the last one.
Call that 10. No, sorry. Call this one 10. You called it 8. Call it 10. Okay, and then delete this one. You don't need this one. Just delete it. Here, delete it right there. Okay, delete it. Like it won't hurt if you leave it, but delete it in this way. Okay, now close. Now you got node number 10. Look, it's perfect. 6.43. You're right in the middle. You understand? So you're okay.
The node I2, node J10, perfect. Ending at max.
That's it. So that's it.
There
So
you go. Okay.
exactly. So now you're
Let me
learning
see
which
this.
is your I and your J. Perfect. You see? Good. I was going to show you how to do that, but I'm glad you know how to do that. There you go. So now you got that pinned. That's
Yeah.
all pinned. You got to go pin this one because this is still fixed to that one. So this is pinned, that's pinned, but you have to go pin this one here or this one, whichever one you want. Then you have to go pin this side and you have to go pin this side.
I don't see your cursor, sir. Can you do
Yeah,
that
we don't see the cursor.
Oh, okay.
Try
Sorry.
now. Let go.
Pardon?
I let go of my cursor. You can try moving it now.
You see my cursor now?
Okay, yeah, now we see it.
So you got to pin it here. Let me annotate. So this way everybody can see it. Annotate. Okay. You have to pin it here, but you don't have to pin it there. As long as it's pinned on three sides, the other side doesn't have to be pinned. You have to pin it here and you have to pin it there. Because see, this member is continuous, but here you can't connect them all as being fixed. So they have to be pinned to each other. You understand? This is pin, 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 pin. This is pin here, continuous there, pin there, continuous and pin there. So you have to go and pin there and pin there and pin there. That's what's left to do. You understand? Then once all your geometry is correct, your members are correct, then you can go and assign the different sizes. Then after that, what I suggest you do, okay, don't forget to put those pins in. And then after that, always work with the visual graphics because it's the best thing to do. Then you take off the you don't need the lengths anymore. You know they're good. You've checked them. You're going to put materials and shapes. Apply. Okay. And this tells you which ones you haven't done yet. You understand?
Yep.
So that's
I'm
the
still
best.
missing a couple.
Exactly. So, okay. So first finish your geometry, then do your, and then after that, now very quickly for the loads. Okay. Like let's say you want to do a load. Remember I told you about the different angles? Like,
yeah,
so let's say, well, first you have to have a load case. So let's put a superimposed dead load. Go create a load case. I want to show everybody where the angles are so that they're all aware of load case. Define. No, don't generate them. The load. Okay, so superimposed. Leave that as dead. That's the structure. Don't change that one. Put SID, superimposed dead load. Then you can define it if you want, but you don't have to because you're not having the program generate the load cases. So leave it like that. And then next one, put a snow load also. Might as well create your snow load right now.
That's true.
Snow, okay. And don't even define it. You don't care. It's gonna, trust me. If you don't want the program to auto generate your load cases, don't define them. Okay. 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 So now go to load. Well, first of all, you have to be on loads here. Go to superimpose dead load. Okay.
Oh, yeah, I have to actually save this.
Yeah, save it as Adriano's good trust design. Well, what's step 5?
Well, I'm following the steps that we do on the design brief.
Oh, okay. You call it step number 5. Okay,
Yeah,
I appreciate
so I got
that.
step 3, step 2.
Okay, okay, great. Okay. Now, here, since they're all the same, pick them all at the same time. The whole top chord. Do you understand? You know, hold on the control button. Pick even the overhangs.
Overhangs.
This one here, like this
Oh,
one here.
yeah, okay. The bottom.
And the other one at the other side. You pick them all. Right click. Properties. So now you're gonna have to go and change this. Okay, so right click on the loads and change it to kilonewtons per meter. Right click, change units, go and kick kilonewtons per meter. Okay. Now, do you remember what the value is?
Minus 0.12, correct?
Okay, I think so. I don't remember.
Yeah.
Okay, so minus 0.12. Okay, and that's it. Now here, where it says angle, call out all the. No, here. See where it says projection? Here.
Yeah.
Call them out. Call them out. See where it says strong axes? Click on that.
Okay.
Press OK. And of course, you're gonna have to adjust your loads. There you go. See, now they're all perpendicular to your member.
So the strong axis, when we select it, it's the member. It goes in corresponding to the.
Like in
member
other
that we
words, it's going to
selected.
put it perpendicular to the depth of the member. Yeah, exactly.
Okay, yeah, perfect.
Okay. Now, if
Okay.
you wanted to go this way, I would have put the weak axis. You wouldn't have seen it on your screen. It would have been going perpendicular to the screen. You understand?
Okay. Yeah.
So, and now for the snow, let's go back. Let's go back to the loads. I just want to show you where the snow is. When you do the snow, you have one called horizontal global. Okay, let's do the snow. Let's just do the snow, for example. Change. Okay.
Oh wait, no. Cancel.
Cancel. So go load. No, you already have the load combination. Just call out the snow here. Here, right here, Adriano. Stop.
Okay.
Here, call out the snow. Do a snow
Oh,
load.
there. Okay.
You've already
confused for a
defined it. Okay, so since they're all going to be the same thing, do the same thing again. Pick them all at the same time. Well, the snow load was 2.5 times 0.6. It's 1.5, right? No, don't do that because it's only the top chord that's got the snow, not all the members. So pick this one, control,
Okay.
pick only the top members.
Even the overhangs?
Everything. There's no snow on the overhang?
No, there is.
Exactly.
Yeah, that's a dumb question.
Okay, pick them all and then right click and okay. And now you're going to be putting minus 1.5 kilonewtons because I just did it. 2.5 times 0.6 minus 1.5. Here under projections, you'll see you have horizontal global. That's the one. That's what the code wants. You press that and press OK. And there you go. Now adjust your load. No, don't do that. Adjust them here.
Yeah, no. I
Jesus. Okay. And there you go. Now you got just now all you have left now is to add the dead load to your bottom chord. You understand? Of course,
it says the snow load on your slides because I screenshot. It says 2.5.
Sorry?
Oh, okay, that's when you add that. Because it says snow load 2.5 kPa.
Yeah, but that's kPa. What's your tributary width for each truss?
0.6.
Okay, so what is, because this is
yeah, you're right.
kilonewtons per meter. It's not kilonewtons per meter squared.
I thought
So
kilometers squared for a second.
okay.
Okay.
So there you go. There, you're on your way. So go back, like now get out of your loads, go back to your structure. Always finish your structure first. You understand?
Yeah, I have to finish
Once your structure, now your load's almost done. All you have to do is add the dead load. Here, it doesn't matter because it's global. You understand? It's going to be at 90 degrees, so you don't have to worry about it. It's only when the members are at an angle you wanted to specify with respect to the strong axis, and that's how ADA puts it perpendicular to the member. You understand? Because in other words, don't you understand that the 2x4, the weight is going this way? And what the program is going to do is it's going to resolve it into the two components, you understand? One vertically and one horizontally.
Yep.
Okay.
Got it.
It's good. I mean, it's nice that it does that. Otherwise, you'd have to break down the components, blah, blah, blah. You understand?
Sure.
Hey, it's looking good. Let's finish it and run the analysis. I want to see if we get the same results.
All right. Do I continue sharing my screen? Or?
Well, keep doing it. Like, just finish. You're almost there. Like, all you have left to do is adjust this one, adjust that one. You understand?
Bottom.
Or if you want, you can work out on your own and.
I'll stop sharing for now because I think Brandon was supposed to share his thing again.
Okay, so let's get back to Brandon's problem. Sounds good. Okay. Hey, Brandon. I like the switching back and forth between ADA and inspection courses and real life situations. So, Brandon.
Yes.
Okay, so let's go back to your drawing and we can take a look at what we need to do. Fantastic. There you go. Oh yeah, I remember this. We were talking about this last week, right? And you told me exactly. Now I remember. Okay. Request remote. Yeah, I want to request. You're gonna grant it to me. Great. And I'm going to also, I want to annotate. Okay, so basically, if I remember from last week, we talked about the beam being right here. Am I correct? In plan view?
Yeah.
Okay. The thing that we didn't know is, are there any loads from the roof? In other words, when we're looking at a cross section, here's our floor. Here's our beam here that's supporting the floor. Okay. here's the exterior walls. Are there any partitions sitting on this wall, on this floor, in this direction, right above the beam?
No, there's not nothing load bearing.
But is there a partition?
Yeah.
Where's the partition?
Over here. So we have, I believe this wall is on top of it.
Okay, but is this wall right above the beam? See, like I was telling you last time,
no, it's not. There's another wall. And there's another wall. Just let me freaking do line.
We're recording all of this, which is good. No, Brandon, what I'm asking you is that, so right now, this is your ground floor, right? And
yeah.
and these stairs are going to the basement because
exactly.
you don't have a second floor. This is just a one-story. This is
only well, this is like the second floor.
Oh, that's the second floor.
Yeah, like if I.
Okay, so let's go. Hold on a sec. Oh, I'm trying to. You're.
There.
Okay, so this is the second floor here.
Yeah.
And then show me the. This is the second floor, and the beam is holding up the ground floor. Is that what you're saying?
Yeah.
Okay, so in other words,
this floor of here.
Okay, so in other words, it's this. So you come in here. This you consider this. There's no basement. This is your ground floor here, right? There's no basement. Is that what you're telling me?
Yeah. Well, like the basement is like this part here, basically.
Okay, so the basement is this part here, and so this is your ground floor here. Do you have a plan view of your ground floor?
I don't remember. It's been a while. I haven't been on.
So that's your basement. Those are your footings. That's your basement. So, and your ground floor. Do you have like the partitions on the ground floor? Because you're saying before that that's your second floor, what we're looking at right now. So what do you have for your ground floor?
There's this here.
That's it?
Yeah, there's no. Well, it's because I only did what we're renovating, so there's not gonna. This is all gonna be open except for the stairs.
Yeah, but right now, what's there now? That's what's important. I know that's what you want to do, but what is there now?
Right now I have.
Because I'll tell you what my concern is, Brandon. Okay, you want to know what my concern is? Okay, my concern is that you might have a partition here on the ground floor.
Mm-hmm.
Okay, which corresponds to the partition that you see on the second floor. And my concern is that there's a good chance that you have a column hidden in that wall that corresponds to a column that's going onto the second floor that's supporting the beam on the roof, and therefore the whole load from the roof that is like, in other words, this is the beam that you have on your roof, and you got a column here because you have, like I said, you have to go in the roof space to see if the beam spans from one end to the other or if there's columns. Okay, and I think that most likely there's columns, and that these you don't see them, but they happen to be hidden in the wall here on the second floor, and they go into the ground floor here. And then here underneath where the beam is, most likely there's a column right there. So look what's happening. This is all being transferred here.
Okay, so basically like over here.
Yeah.
Like these are 2 rooms. And like over here is a closet. So where the beam up top would be, it goes right in the closet and it's open to it, so there's nothing supporting it. That's on the second floor. Like the stairs right now are like this.
No, but we saw the second floor. You had a picture of the second floor.
Yeah, but the stairs are moved. Like the stairs are like this, and now they're gonna be like that.
Okay, I understand. But see, Brandon, you have to draw what's existing.
Okay.
Whenever you're doing any renovations, you have to draw what's existing so that you can get an idea of how the structure might have been built. You understand? Because me looking at this is very misleading. This is what you want to do, but it doesn't mean that you can do it. Doesn't mean that you can all of a sudden take away things, and all of a sudden you're realizing that you're taking away columns, Brandon, and you're taking away, you understand? Or columns that are coming down through the walls. You might not be seeing them, and then all of a sudden, like your whole analysis is going to be incorrect. You understand? So go ahead.
Yeah.
Okay.
So over here is like the stairs. Then you have like there's the wall here. The wall there. And over here there's a wall there. And over here's a hallway. And then
Yeah, and now show me where the beam is underneath. Change color.
the beam would be about over here.
Exactly. So there's a very good chance that there could be columns sitting in here somewhere. You understand? It could be a very good chance that there are. You understand? Transferring the load from the roof down to the basement. And I wouldn't be surprised, you know, like, and I wouldn't be surprised if you go in the basement, you should measure where those columns are located, and then go on the ground floor and see if where those columns are located, if you have some partition, you know, if that partition is like, so this is my beam here. So I need to annotate. Okay. Okay. Yeah, Sam. See, Brandon, you're showing me that this is a partition here like this. I don't care about this partition here. I care about this one here, the ones that are running parallel to your beam. You follow, Brandon?
Yeah.
Okay, because the ones that are running parallel to your beam, you don't know what's happening inside that wall. Okay.
Yes.
So the wall might not be load bearing, but all of a sudden there could be a column that all of a sudden, like for example, if I do a cross section here, what I'm trying to make you understand, if I do a cross section here, okay, you told me that this is what you have. You said that you had rafters and you had a big beam in here that's supporting your roof. You understand? And you were saying that that beam goes from there to there, and I said very unlikely that it's doing that. Okay, I suspect that the fact, unless this is a big glue lamp that can actually span this. If that's the case, well, that's the first thing you have to do. You have to go into the roof space and see if this beam that you have at the roof space, like, and this is sitting right above that beam that you want to modify. So you have to go and check to see how this beam is being supported. Okay. So in other words, if we do a roof plan, this is my roof plan. Here's my beam. Here's my rafters that are going down. Okay, I have to determine, do I have a column only there and there? And if you go into the roof space, in other words, do I have a column only here and here? If that's the case, then you know there's no load from the roof coming down onto that beam. Okay, that's number one. But at least we know that there's loads coming here. But you might not have to modify that column. After that,
yeah.
You understand? So
yeah, so I have.
Go ahead.
I have pictures that my mom took for.
Did she go into the roof space?
That's basically what it looks like. It's like the roof is on an angle here, and goes all the way up here, and runs across.
Okay, but now I'm trying to orient myself. Okay, I'm trying to orient myself. Okay, so right now, this is supporting the roof. Is that what you're telling me?
Yeah, that's the roof up here. So basically, where you would be right now, like let's say this is the building.
Yeah.
So.
Always use the beam as a reference point. Like show where the beam is, in which direction. That's important.
Yeah, so the beam is there, and then there's like the little kitchen place that's here.
Wait, no, before, no, Brandon, where is this right now with respect to this?
On top of it, about.
It's approximately on top of it. Is that what you're telling me?
Yeah.
Now, this here and this here, is this the exterior wall here?
Yes.
Okay, so in other words, I'm looking at, this is the exterior wall. So here this beam is supported by this masonry wall.
Yeah.
Where is this point here on your plan? This one, this point here, where is
That point would be approximately here.
Okay, so that's why you have to be careful, because if it's here, there's a column in there. There has to be a column in there, Brandon. You understand? So like here, there's a column that goes down, and therefore does that? It's probably gonna. It probably goes and sits on top of the beam.
Like it just goes in there, and behind this place here, that's the closet space.
No, but I'm asking you exactly. So I'm asking you in terms of your plan view here. This point here, right here. See where I'm doing the X here?
Yeah.
That's right there.
Yeah.
Okay. Now, so this is the beam that's supporting your ceiling, right? The roof.
I think, but I think my parents told me it's a fake beam, so it's not an actual like
So
supporting member.
you don't even know if that's the real structural beam. Is that what you're saying?
For the roof, I don't think this is the I don't think this is structural. I think it's just aesthetic.
Okay, so you're gonna have to go see the structure of the roof and see how it's supported. Without that, Brandon, we can't do anything. Like I said, you have to look at the top, okay? And you have to look. It's very simple, okay? You go to the top and you have to see how the loads are coming down into the structure. Okay, the load path. Okay, so for example, if I'm looking at a plan view of the roof, here's my beam. Okay, so that I understand that all the roads are being supported by this beam. Now, is there a column only here or here? Or is there also a column here? That has to be determined, understand? Because if there's a column in between, well, that column has to go all the way down to the basement. It can't just sit on the floor. You follow? And if that column that's supporting the beam in the roof happens to correspond with the column that's underneath the beam, then those two columns, that load is getting, you understand? So in cross section, what's going to happen is that here's the beam that's supporting my roof. I know I have one at this end. I know I have one on that end. Okay, guaranteed. Okay, otherwise the beam would fall. Now, do I have one here in between somewhere? That I don't know. You understand? But let's say, because this is the thing about walls, you have to be careful. The walls could be hiding where the columns are. Okay, so you can have a column or you understand? And then all of a sudden, so this is the beam that you want to modify here that's supporting the floor that you want to modify. You understand that? Because now, if this column here happens to fall on top of the column that you want to modify, because here you said this is where you had your three columns, you understand? And if you want to remove this column, well, it becomes very critical because all this load here has to be carried by the beam that has to be transferred here. So it's a completely different analysis. So, I mean, everything is doable, but without the information, you can't do anything. And we're not going to second guess it because it has to be done right. So you have to start by looking at the roof. And then from the roof, look on how the loads are coming down. And then after that, like where the walls are, well, are they covering up columns? In other words, did they bury it? Most likely that's what you usually do for aesthetic reasons. You tend to put the columns inside the wall so that they're not apparent, okay? And then here at this here, they plop two columns here, okay? And so, because if you're telling me that there's nothing on top of this beam and it's just a floor, well, it's it's simple, but but if that's not the case, if all of a sudden this is the case where a column comes on top of another column and you want to remove this column and you're analyzing this only for the load of the floor, what's actually happening is all the load of the roof is coming down also on top of that beam. Well, this is going to be your analysis. You have your beam, you have a support there, you have a support there, you have a concentrated load of all the loads that are coming from the roof, in addition to the floor that's being carried by the beam. So see, this is going to be a big force here, and it's going to completely modify your MF, completely modify your VF, completely modify your deflection. You understand? So without being able to establish this load diagram, I mean, we can't do any analysis, and we can't see what has to be done. You understand? So the more information you get, Brandon, like, do you go up there at all?
I do, but I haven't, I don't go that much.
Can you get up on the roof space at all? There must be a, like, first of all, is it a cathedral roof or is it, is there a roof attic on top?
There is no attic.
It's a cathedral.
Yeah.
And this beam here is right in the middle of that, like this beam here corresponds right where in about the middle of the, in other words, if I look at the pitch here of your house, this beam is sitting right here like this. Is that it?
Yeah.
Then this is not aesthetic, this is structural. If you're telling me that you have rafters, that's a structural beam. Because that's what is actually supporting your rafters, you understand?
Yeah.
So that is a structural beam. It's not aesthetic. They finished it. It's nice. It's probably a BC fir beam, you understand? And it's probably a 6 by 12 or 6 by 14. It's a big beam, trust me, okay? But what's happening is the rafters are being supported by this thing. So at least here you have a good idea. Go back to the picture where you see the view, the beam from the side, you see? So here you have a good idea that all the roof load here is going, at least, you know, there's none, on this part of the floor, you have absolutely nothing. Because that's where your beam is, it's right here, right, somewhere?
Yeah.
You see, so now we know that here we have nothing because it goes from there to there. The columns that you want to modify, do you want to modify them in this area here, or do you want to modify them in this area here? Which area do you want to modify your columns?
Stop it. I think it would be in this area here.
In that area there?
Yeah.
Now, do you know this distance from here to here?
I do not.
Okay. Do you know where the column is here with respect to this wall that you want to modify?
No.
Okay, so that you need to know,
think you
because
did.
then we can see if we know where this column is, because let's take this as being the reference point here, this wall here, this exterior wall, right? So if you can measure where the columns are, for example, if this happens to be 20 feet, right? And this column here happens to fall at 15 feet, well, we know that we have nothing here because the beam's carrying everything. You follow? So as long as we're not going to go modify anything in here, it's not a problem. So do you follow what I'm saying?
Yeah.
So like I said, so you go measure from there to there, okay? And then go in the basement or in a, wherever, the ground floor, and measure from this wall here where the columns are. And then in plan view, see if this beam here happens to correspond where the beam is underneath the floor. It could be, most likely is, you understand?
Okay.
And from there, then from this, I'm glad you got this picture, because see, this picture tells me a lot, you understand? It tells me there's nothing on the roof coming down in this area here. So all I have to worry about is the loads of the floor here, you understand? And these partitions here, you understand?
Yeah.
So that's something that we'll be able to calculate very easily. And like I said, if you only want to modify this column here, and it doesn't happen to be, it's away from this end here, I don't care, because we're not going to go touch this part of the structure. So therefore, all I have to do is add the weight of these two partitions in my calculation. You understand?
Yeah.
That's it. So that's why it's important. So the key thing that I'm trying to stress here, Brandon, is that geometry is everything. You understand? So drawing an existing plan is key to making sure you don't make a mistake. Okay? I know that you were drawing the modifications because you want to see what it's going to look like modified, but before you get there, you have to see how structurally it can be modified. It's like if you weren't going to touch the structure at all, fine. But since you do want to modify the structure, since you do want to remove a column, it's very important to know how the existing structure is behaving right now. Because, you know, you definitely don't want to go take off a column without knowing what are the loads that that column is actually supporting. You understand?
Yeah.
So can you do that? Get that information?
Sure.
And then we'll keep going, Brandon. We still have another 7 weeks before the semester is over. So, Fair enough. Okay.
Yeah.
Okay. So,
Sir,
yes.
I have a question on ADA.
Okay. So let's go to ADA. Hey, we're
Here,
we're still recording this, huh? Do you think I should put this on pause? No, I'll keep recording.
Okay. Can you see my ADA?
I see your ADA.
So I added when I add this on, let's say, on this side, it doesn't allow me. It says here the number of selected objects has already been assigned. What is, like, I don't understand what does that mean.
The number of the selected object has already been assigned to another object. Okay, so close that. Close that. What is it that you want to do exactly?
I'm just trying to pin it, like.
Okay, so you take this member here, right? Right click.
Yeah.
Properties. Okay,
Yeah.
so do you know your node numbers first of all? See?
Here we go.
Okay, so this is node, this is
number one,
and that's number 2. Okay, so I is 1. Okay. Okay, so go ahead, click on it.
So number 2 and 1.
I is 2, so therefore you want to go here, like. Okay.
Wait, if I is 2, so yeah, so I have to go like this, basically, because I want it to be, no, I want it to be at 1. I'm sorry, never mind. Wait, let me see. F2. Yeah, so I want it to be at J. Yeah. I have no idea, actually.
What I have no idea what you're doing. Oh, first, okay. Okay, let me try something. I'd like to hold on a second. Request remote control request.
All right, approved.
I'm approved. Okay, so basically, so everything. So you were able to do this. You were able to do that, right?
Yeah.
Okay, and like I said, this looks good. Can I just check something? The height you got here, is that the right height? I guess so, right?
Yeah, it is.
Okay. This is good. That's good. That's good. That's good. I'm just doing a very quick. Okay, so here. 2x4 SPF. Okay, member number 2. Oh, this is where did you touch this? Invert?
No, I did not touch. No.
I is 2, J is 1. Well, let's invert it. The number of the selected objects has already been adjusted to another object. Oh, so what happened here? What happened here? So this is something that I like to know what I like to know what you did by accident. And
interesting. Actually, I think, yeah, because I selected them like this.
Oh, worst thing. Yeah, worst thing to do. Yeah, okay.
I think that's what I did. I selected them and then I pressed like this and then I went like here and did that.
Well, I mean, that's okay. That's not a problem because they all have the same end conditions, you understand? And you were able to select them by crossing. So that's not a problem. I'm trying to understand, why are you getting, what did you toggle on or off that is giving you that error message, you understand? And that's what I'm trying to understand. So I'm trying to understand what it is exactly. SPF number 1, number 2. That's all good. That's all good. That's all good. Bending.
Because it's not only this member. Like if I try it on another member, I think that's what's going on. So like I think there's something wrong.
Well, there is something wrong because you're getting the number of selected objects has already been assigned to another object. Oh, I don't know, like.
Cancel.
Okay, so I'm trying to see what the Omar, like, I'm trying to see what the we don't care about the links, that's for sure, for now.
Oh, I see. Never mind.
I
Oh
see.
my
I see what the problem is.
Yeah, I see what is that. Okay, I saw. I just saw it.
Okay.
Yeah.
Okay. So
Yeah,
you understand?
okay.
You understand what the problem is,
Yeah.
Omar? Okay.
Oh, sorry. That's wrong.
Okay. So that's where the problem. You saw it, right?
Yeah.
Okay.
Members. So I have members called 1 and 2 and 3. Oh.
So change this one. Okay. You can't have the same number. You understand?
Yeah. This is between. So I have 12, 1, 2, 3, 4,
Yeah.
5, 6.
So that make now double click on this one and try to do it now.
Okay. All right, it works. Okay.
Of course.
All right.
You see, Omar, I keep telling you guys, use the visual graphics whenever you're doing anything, you understand? So that you can see right away if you're doing something wrong. I don't know why you guys are trying to keep this all in your head. It's pinned, Omar. I did it for you.
Yeah.
How's that?
Thank you. Thank you.
So aren't you happy I found your mistake?
I'm happy. All right.
Okay, so do you understand the importance of keeping the visual graphics on as you're modeling? That's what you should have learned from this incident. You understand that keeping the visual graphics on your node numbers and you understand, and your member numbers, you would have seen right away that your member numbers, like the program, Omar, it's a spreadsheet. Do you follow? Okay.
Yeah.
And all of a sudden you're telling the program, take this as number 1 and take this number 1. The program say, I can't. I have to choose one. I don't know. And if you're going to run your analysis, you're going to get an error message. It's 2 members have the same number, so I don't know what to do anymore. You understand? So thank God that you saw the glitch by having to try to change the end condition to member. Otherwise, as soon as you were running your analysis, you would have had an error message.
Okay.
You follow?
Right. Thank you, sir.
Okay. So like I said, like I always keep my visual graphics on until my model is completely finished. And then after that, I move on to my loads. And once my loads are completely on, I move on to my load combinations. And then I move on to my analysis. So systematically, and guys, do your sketches in front of you. Don't try to do it in your head what the dimensions have to be. You know, write all that information down on a sketch and then go put it into the program. The program just wants input. It doesn't want to do anything else. Wow, it's already 5:49. Aren't we supposed to finish at 5:30?
Sir, I have a question about.
Go ahead, Alex. Go ahead.
About Brandon's situation.
Yes.
Let's see if the beam was connected to joist hangers, and you want to add the channel. How would you disconnect the joist and add the channel?
Oh, you mean if the beam's side loaded? Is that what you're saying?
Yeah, exactly.
Oh, see, that's what I'm saying, Brandon. If that's the situation, then we'll have to look at another way of reinforcing the beam.
Okay, got it. So the channel's going to work in that case.
Exactly. In other words, if the beam is side loaded, right, then we're going to have to find another solution.
Okay.
But if the beam is top loaded, the easiest solution is just by putting 2 channels on each side. You follow?
Got it.
And what I'm trying to stress here for all you guys, that without knowing the constraints, you know, I could come up with any solution, but by knowing the constraints, then it imposes me certain choices that like, so you brought up a very good point, Alex. Like here I am assuming that it's top loaded. You understand? You follow what I'm saying? But you're right. It could be side loaded. And if it happens to be side loaded, well, then we'll look at the options of how to reinforce it. Okay.
Okay.
It's going to be a little bit more, let's call it tricky to do, but everything is doable. So you brought up a very good point, because the other thing that we could look at doing is maybe just putting a channel on the underside of the beam. and see if there's enough stiffness in that. Anyways, like, it's going to be interesting once we get to see the details. But good point, Alex. Very good point. Here I am assuming that it's top loaded. It could be side loaded, and if that's the case, you know what we can do.
What can we do?
Well, here, I'll show you. Okay.
Could you add angles on the edge of the beam, like on the other underside?
Sorry?
Can you add like angles, steel angles?
Oh yeah, well, see, the thing is, it's all going to be a question of, like, for example, like here, like what you're telling me, that here's a built-up beam. I'm doing a cross section now, right? So here's a built-up beam like this. And that the joists are side loaded, right? Agreed?
Yeah.
Okay. So if all of a sudden we cannot reinforce the wooden beam because the joists are here, okay? It all depends on the headroom that they want to keep in the house, Alex, okay?
Yeah.
We can put a steel beam right underneath here.
Okay, got it. But that would drop the ceiling by quite a bit.
Well, no,
Pretty much into the box vent.
8 inches or something. You understand?
Yeah.
What do you think of that solution?
Yeah. I don't know about the look of it. You probably have to like make it a box around.
Oh
it.
yeah, then they're going to make a bulkhead and cover it up. They might lose 8 inches, but that's, to me, the simplest solution. You understand?
Got it. Okay.
But before you do this, I would still jack up the floor. You understand? And make sure that the floor is jacked up. Put the steel beam and have. Otherwise, if you don't jack up the floor, if this beam is slightly overstressed right now, okay, when you put this on and it starts to deflect, this thing is going to cause all kinds of cracks upstairs. Do you follow?
And would you bolt it through the flange?
What, here? Well,
Yeah.
you should fasten it. You should fasten it to the underside of this beam so that you can lightly support the top flange. You understand? But if you don't fasten it, then you take the LU going from column to column, and you design it with a longer LU.
Oh, I see what you mean. Okay.
You understand? So it depends. If you can't afford to have a big beam in here because you don't want to lose a lot of headspace, then you fasten it. You know, you look like, for example, if you decide to use a W200, which is 8 inch by 19, let's say, right? Because they're not big spans. Okay. So you know that you're losing 8 inches, but then this, I think the LU for this is something like 2 meters. Okay. So therefore, what you do is you're going to fasten it at every 4 feet. Then you know that your LU, you've taken care of your LU. You understand?
Okay.
So the fastening would be to lightly support the beam so that you can shrink down your LU to whatever you need. You understand? You want to hear something interesting, Alex?
Yeah, sure.
Okay. Somebody came to me. Okay. What they're doing is they're this is okay. The guy he wants to build himself a shelter. Forget it's a shelter for his equipment because he's an excavator. Okay. In plan view, he's got a steel container here and a steel container here. This is in plan view. Okay. You know what I mean by containers?
Yeah.
Okay, because he uses this to store his materials and
like
stuff.
A cargo container.
Yeah, exactly. Guys, if ever you want to make yourself a trailer home, go buy yourself a used container. Structurally, you can't go wrong, and they're very cheap. Okay, so this here has a span right now of I forgot what he told me. I think it was 34 feet. Okay, 34 feet. And what he wanted to do is this is what he's going to do. Like and this is and in this direction it's 40 feet because these things are 40 feet long. These containers, you know that when they're sitting on the truck, right? So what he wanted to do is he wanted to put a steel beam right across here, supported at this end and at this end. Okay, and he didn't want any columns in between. okay? And here he already bought the joist, and here he's spanning 15 feet, and here he's spanning 19 feet, okay?
Okay.
So he designed the beam, and he ended up with a W. I'm trying to remember what he designed it for. I think he ended up with a W610. Okay, 610 by, I forgot what it was. I think it was a 101 or something. Anyways, it was a fairly heavy beam, okay? I think the beam was going to cost, just the cost of the beam, because he was going to install it himself, the cost of the beam was going to end up costing about $1,500 just for the beam, okay? So anyways, just to give you an idea. So what I proposed to him was this. I might as well, hold on a second. I want to, hold on, because this shouldn't go on the, okay, I'll be right back, Alex. I just want to put this on pause, okay? Because this shouldn't be part of the, people want to watch the video, and I want to bore them with this, okay? So where was I? The whiteboard, right? So he ended up with a, I don't remember, like it was a fairly heavy beam, you can appreciate, right? A 40-foot span and this and that, right? Okay. And the reason why he wanted to do this, and he's going to have 2 overhead doors here, so he can come in with his equipment and freely, you understand, move around wherever he wanted to without having an obstruction here. You follow what I'm saying?
Yeah.
Okay. So what I proposed to him was this. I said, well, why don't you do this? And well, I think the beam ended up costing about $2,000. I'm trying to remember. Anyways, so what I proposed to him was this. I said, when you come in with your equipment, you can't never drive around here. And here he was planning to put 4 foot of shelves anyways back here. Okay. You understand? So he wasn't going to use, so in other words, his real circulation area was all in here. You follow?
Yeah.
So what I said, that since you're circulating generally in this area here, why don't you put this column 5 feet away from the wall and 5 feet away from the wall? So right away, you're down to a 30-foot span instead of a 40-foot span. So, like, WL squared over 8, right? So if I can take off 10 feet, I'm already saving quite a bit in the moment. So yeah, that makes sense. You follow what I'm saying? Because even if he comes in with his equipment, he can never get into this area here.
Yeah.
So the first thing I did, the whole Gerber system of cantilevering to redistribute the moment. So that was the first thing I told him, right? So I told him, number 1, let's put the column here and let's put the column there. So that right away helped to lower the span. Then I said, in the wintertime, when you store your equipment, do you need to circulate? He says, no. He says, well, in that case, why don't you put a column in here only for the wintertime? You see?
What about in the summer?
And in the summertime, you can take it off. And in the summertime, the beam was good for 20 pounds per square foot, which was
because there's no snow.
Exactly.
Okay, got it.
So we came up with a solution of having a temporary column there, okay, that is going to install for the winter. So when there's a snow load, it can hold up all the snow load. And in the summertime, he takes out the thing and it still gives him 20 pounds per square foot for the rain load.
Huh, interesting.
And he came down to a beam that only cost him $600.
Nice.
Isn't that nice? So you like that solution?
Yeah, it's interesting.
Of a temporary column? Because the column is only necessary when he doesn't need to circulate. And when he needs to circulate, the column is not necessary because there's no snow.
Cool.
Nice, huh? So this is like, these are like, like this is just, and what I really, when I made him realize that just by offsetting the column, like, because he wanted to hide these in the walls, right? They said, what are you worried about? It's a goddamn shed. It's not even a house.
Yeah.
So as soon as I told him about, like, you're never, like, when he told me, I said, you'll never be able to circulate. Even if you turn almost 90 degrees, you still need a radius of at least 5 feet to get in here with your equipment, right?
Yeah.
So I said, so this is, I call this a non-circulating area. And I said, put your columns there and there. So right away, we were able to save, And then what I did for him is, of course, I did the whole analysis, snow load, 50%, 100%. I did 6 load cases and every that, And then of course with my spreadsheet, I was able to just throw it into the spreadsheet, and it gave me the size of the beam, you understand? And ended up saving him about $1,000 just on steel, you know, which is and the other thing that was nice is that he's going to be building his walls right on top of this right here, you know, like, and these are going to be, he wants to make these at a 2x4, you understand? So he's going to be supporting the joist on like 2x4 walls, and I checked to make sure the 2x4s were ample to support. And I said, what I also told him, I said, if you're careful, because if you're careful and you know you're going to be spacing these at every 24 inches, all right? I said, if you're careful and you know that your first joist going, and you're going to go at every 24 inches, if you let the stud in the wall fall right underneath the roof joist, you don't have to double your plate. He said, yeah. It says yes. And even the code says that if the stud in the wall falls directly underneath the joist, you don't have to double your plates. You're going to save yourself 80 feet of 2x4 just on the top plates. You understand? So he said, oh, great. Okay, thanks. You understand? So I did everything.
The wall is on the outside of the steel container.
Pardon?
The wall is on the outside of the steel container?
On top of the container.
Oh, on top of it. Okay.
Alex, this is the container here. Here, let's clear this whole drawing. Okay, so here in elevation, this is his container here sitting in his yard. And I think he had purposely put the other one that far away from it, you understand? So basically what he's going to do is he's going to be building the stud wall here, and he's going to have a slope roof. He's going to short a wall here, and he has this beam in here.
Okay, got it.
You see, and it's going to be doing this. And what we did is that to get him the lowest, I calculated, you know, I even calculated for him to laterally brace the beam so they can minimize, you understand, the size of the beam, and came up with a very easy solution, you know. So, and that's it. And now all he's going to have is this, you know, this column in here, which in the winter time he'll put up for the snow, and then in the summertime he takes off, and he'll be able to circulate in the space. And he's gonna have an you know, an overhead door here, a man door on this side, and an overhead door there. You understand? That's what he's planning to do.
And I'm guessing he has doors within the shipping containers.
Pardon?
He probably has doors in the shipping containers, correct?
Well, here, yeah, these, like the doors, I think they're here, you understand? Like they're right here, the doors for a shipping container, you understand? Like
Okay.
the ones that open this way, you know? But this is his shipping container. They're like side by side. So he's saving all this wall here, right? Because he's using the wall of the shipping container. He's just building these little dwarf walls on top. And this is very strong because this is where all the steel structure is for the shipping containers, right?
Yeah.
So that's perfect, you know. So he's applying the load right where the containers can take it very easily, because you know, like when these shipping containers are piled in a ship, you got like 20 on top,
exactly,
right?
Yeah, they have to support them all.
So these things are super strong, right? And believe it or not, if I was a cheap white trash and I wanted to move to Florida and live in a trailer home, I wouldn't buy a trailer. I'd buy one of these things and convert it to my house.
Well, I've seen some videos where people just like stack them all together and weld it and make a house out of them.
Probably, yeah. Well, I know, like there was one guy, I saw this on a program where this kids, what they were doing, well, kids, young adults, okay? They were buying these containers, right? And they were converting them into, let's say, mobile trailers for the construction sites, so that the workers that are working in remote areas, the contractor can just ship them up there and they have a place to stay, and you wouldn't have to pay for a hotel for them to stay up there.
Okay.
That was smart, you understand? So very inexpensive, because these things are literally like you're paying for the value of the scrap metal. They just want to get rid of them. And the shipping companies want to just get rid of them, so you can pick them up at a very good price, you know. So I thought it was pretty good what we came up with as a solution, and now we'll see what he was happy. He ended up saving about $1,000, and I figured, why not, you know? So that's what I like, you know. Like I like sometimes, Alex, like thinking of solutions that are, you know, fun, you know, like I can tell you.
I find it really interesting. It's good from the norm of what we usually do.
Well, I mean, it's like taking what we do and then just expanding on it, you know, it's because it is basically, you know, like understanding, oh, how can I reduce the span? Because the span is very critical when I size the beam, you know. So like it's making those connections and then realizing that are we going to end up with a better option, or are we at the same, you know, that's all it is basically. And the thing is that you know, I'm pretty sure that there could be like there's 1,000 solutions, but he started off with the very typical solution. You understand? Like he just put his beam, he put the column at the very end. You understand? And then he said, "Oh shit, that's going to be a very expensive beam." You understand? When he started to calculate the snow loads on everything. So his objective that this is just a shelter for his equipment. You understand? So he wants to spend the least amount of money to create the shelter. You understand? He just wants to be able to keep the snow off his equipment during the wintertime.
Yeah.
I thought.
Thank you. That was great.
Okay. So listen, did I ever send you that catalog for the?
Yeah. For the,
okay, you did get it.
joys.
Yeah, you went through it. Did you get a chance to see
It's
it?
all Imperial though, right? So
yeah, but it's all the same stuff. Just remember. Just like I know it's all in Imperial because unfortunately a lot of stuff is, well, first of all the lumber, so yeah, I don't know if they have a metric one, but the conversions, Alex, is very simple. Google convert.
Yeah, exactly.
It's the easiest way to. I do that myself, so don't worry about it. Like mind you, I've been doing it for years. You understand? Like first of all, I grew up in the imperial system. I had to switch over to the metric, so there's some of them I know like the back of my hand. You understand? But sometimes like I don't remember, so I just go to Google and ask for the conversion. You know, so. The only thing you have to be careful about when you're going from imperial to metric is, especially when it comes to section modulus. You understand? That's very important. As a matter of fact, there was one situation I was involved in. I got to go because my wife's going to kill me. But the guy, this is the problem when you have programs that you can work in imperial and in metric at the same time. Okay. And what he did is that he was designing something, and when he wanted to calculate, you know, the program worked in both imperial and in metric. So what he did is that he put all his loads in imperial, and he put all the section properties in metric, but it was totally wrong because metric uses a 1 meter to calculate the section properties of sheet metal, whereas imperial is 12 inches. So he had grossly underestimated what the materials can, and I told him, I said, there's your mistake right there. He says, wow. And end the story, you understand? So that's the let's call it the perils of, you know, when you're going back and forth, you understand? Like I know that ADA, you can go from imperial to metric, right? But you got to be careful because sometimes you don't realize the imperial, especially when you're doing something that is custom, and that so you got to be very careful when it comes to units. And that's why I keep stressing in class, like it doesn't hurt to say 12 inches is equal to 1 foot, you understand? And put all your units down and cross out your units, because it's very embarrassing if you make that. And then here it was not only embarrassing, this thing ended up costing about $120,000 to fix, you understand, on top of that. So the units for me is like, even if it's done on a computer, I always make sure my units work out. Otherwise, the whole thing is not worth anything. And that was a very good example of where, you know, in the computer program, accidentally using the wrong units for the wrong reasons, you know. So on that note, gentlemen, I'll bid you all a good night because it's already 6:10. Not that I don't mind staying here until my wife tells me it's time for supper, but hey guys, enjoy your spring break, right? I hope you make the best of it. And in the meantime,
not much of a break. It's going to be doing a lot of projects and studying.
Yep, well, a lot of projects.
No, I know, but I'm saying at least you like the smart ones are going to take advantage of it. Like I'm sure you're going to take some time to yourself, right? You're not going to be working constantly, but
yeah, sure.
But I know that you should not leave. Like don't Like, in other words, be productive, but at the same time, you should take a little bit of a mental break from, you know, at least you won't have to put up with the lectures, right?
Sure.
And
We'll
the
have more
labs.
time because of that too.
Exactly. So enjoy yourselves, guys, and we'll talk to you in about, well, a little over a week, right?
You too, sir.
Yeah.
Okay,
All right,
guys.
thank you.
You're
Bye.
welcome. Talk to you soon. Bye-bye.
Thank you. Bye bye.